disagrees with experiment, it's wrong. And that simple statement is the key to science. It doesn't make a difference how beautiful your guess is. It doesn't make a difference how smart you are who made the guess or what his name is. If it disagrees with experiment, it's wrong. Simple statement.
100. Yeah, look, they said that I couldn't do it, so I went and did it. W's only, you know I've been winning. Top of the world, the globe is spinning. If you know, I've been on a what? Mission. Go. Okay, let's get it. Got a little time on my hands like a wristwatch. I don't got time for the brakes and a pit stop. Race through the gridlock, take it like Chris Rock. Right to the chin, still win. Heavy metals like Slipknot. Got the driving, I got tunnel vision. I just hit my stride the way I run the business. I've been making paper like I'm Dunder Mifflin. See the end game, I got one division. Look, I don't ever bother with a critic. Hit him with a chronicle of Riddick. Boom, bottle full of Ritalin. I hit him with a little bit of riddle me this, riddle me that. My bad, fell asleep at the gas. No time to wait though. Elon Musk, I'm trying to bankroll. New Tesla just cause I say so. Electric whip like Ivan Van Gogh. I just did it. W's only, you know I've been winning. Top of the world, the globe is spinning. If you know, I've been on a mission. Okay, let's get it.
I've been on a mission like totally spice. I'm a baddie, she bad, but she totally nice. Nails are blue and her toes feel like white. They compli niet met jou, dat is zo voor mijn lijk. Je knew it for sure, but he...
What is up, party people? All right. Make sure you guys let me know if my audio is good. Sorry about that. Morning smoke sesh. All right. All right. See if everything is good. All right, so today's going to be an interesting one. I don't really have much planned except for this very first part, or not even the first part, just a certain thing to talk about that happened last night in the ummmmm server. We were graced with Shane's presence, so we're going to kind of go over some of the stuff that was said there. Let me see what's going on. I'm trying to figure some stuff out. I fixed, or I don't know if I fixed it, but I definitely know why my audio was sounding weird yesterday between the panel and me. So it should be much better today. I think we will have a few people on today. I have Toro. He's in the Discord. Just so everyone knows, if you want to join the panel, be part of it, you can join the Discord. The link is in the description. Make sure you guys like and share so we can get some more people here to discuss what's going on. But let me give you guys a basic idea of what we're going to do. All right, so awesome. So I'm going to give you guys a basic idea of what we're going to be talking about in general with the whole stream, because I wasn't really planning for this until last night happened. We're going to start off, basically, I want to talk to Totoro. He said he doesn't have much time, so I wanted to make sure this is the very beginning of it. Last night, Shane came into the server and graced us with his, I don't even know what you call it, I guess, claims of specificity. He didn't say that, but I know he says it a lot, so I like saying it. Yeah, so basically what ended up happening was it was a conversation between Totoro, Nasha Shill, Shane, Demon Stride, or as he goes now, Mr. Stride. It was a conversation about gravity and all the forces and how we measure things that fall, etc. Okay, cool. Awesome. Yeah, I'll be in the Discord in a second. Yeah, so basically basically a recording, and we'll kind of go through the clips of how Shane explains these things. And then when I was asking him, I was kind of, because again, guys, I definitely am not the brightest mind anywhere near it in this community. So what ends up happening is I have a lot of questions. If I hear someone say something that I don't get, I want to understand it. And to understand it, I really, really have to ask for details. And in doing so, I couldn't get a grasp on what Shane was saying. Totoro was there, and what ended up happening is I got the opportunity to go, hey, Shane, it sounds like you're reading a script. If we were to have a conversation and break it down, can we do that so this makes more sense? And he seemed okay with it, but then he just went into it some more. So what I figured I wanted to do is, because our friend here, Totoro, he's a very smart dude. He's actually able to break these things down. Now, here's the fault with Totoro. Ready for this? He's so smart, he doesn't understand. He can't explain it to the layman, but I'm going to help him do it because I want to understand it, and he understands it, but I know what the layman would understand. So we're going to try to pick his brain to do so. And the reason I say it like that is because when I listen to Shane do these things, I'm sure everyone's heard it, right? He goes into this hyper speed script, and it's not like you can have a conversation because he needs to get through that. You can't ask him questions from the beginning of it because he has to finish it before he can stop talking. And I figured if I can play one clip, right? All I need is one clip of Shane saying what he thinks this is what's going on. And then I figured we could do like a whole live stream basically off that one 10, 15, 20-second clip, just trying to break it down. So I can try to understand what Shane's trying to say. Because he's saying that gravity is not real, but I figured out what it is. But I can't figure out what it is because every time I ask him to break it down, he just runs into a script, not an explanation. So I figured that's what we're going to do at the beginning. The second thing I wanted to talk about today for sure is basically where the final experiment is today. Because I kind of feel like after the Awake Soul interview, the whole hype around the final experiment started going down. And then I want to talk about the one he had with Dale, because that by far was, and remember, I interviewed Duffy, right? I think if you took my interview and Dell's interview and you meshed them together, it would be the perfect interview. And I say that for this reason, because Dell, there was absolutely the final experiment questions, but Dell also went into like more the personal whys, right? Like what he thinks and what Dell thinks. And I'm not sure if anyone saw it or not, but Dell and Duffy feed off, like they work off each other very well. It was very odd. So we're going to talk about that. I think my friend Riggs said that he may have someone he wanted to debate about something. I'm not sure 100%. This happened maybe 10 minutes before I started streaming, so we're going to see how that goes. Again, because we're talking about stuff, but it's still an open panel, guys. So if you guys want to join and give your 2 cents about whatever we're talking about or watching, more than welcome to join Discord. I will be watching the chat. But let's get to it. Let me get to the Discord. So I'm just ranting myself. And then that way you guys can also hear. Actually, I can still hear it. All right, give me a second. I got to get over there. There we go. What's up, sir? How you doing?
Hey, how's it going?
Pretty good, pretty good. This is not going to be a very structured thing, but that's how I like it. And
Sure.
I figured, with the chaos that happened yesterday, not chaos. I don't know if you noticed the title, but I think what Shane did last night was my title is a perfect description of that. It's not word salad.
Yeah.
It's perfect. It's vector salad, right? Because
Pretty much.
so we can kind of get a blanket idea of this. Shane, so and you can answer yes or no, I guess. Shane believes that when you drop a lighter, or basically, let me start over. When you drop a lighter, you can derive that it drops at a rate of like 9.8 meters per second squared, correct?
Mm-hmm.
Okay.
Yeah.
What Shane is proposing is that he figured out something besides gravity that equals basically the same thing.
Mm-hmm. Yeah, I guess, sort of.
Okay, yeah, okay. And in doing so, the natural human intuition of someone that is listening to this goes, how did you do that? And that's kind of what we started, that's what we ran into the brick wall last night, right? When it was, now, how did you do this?
Yes.
Okay, so I'm going to do something. I'm going to give him the benefit of the doubt because here, not, I'm not really going to give him the benefit of the doubt, but what I'm going to do is I want to show everyone, and I'll share it on Discord so that you can see it as well. But those equations that Shane was showing last night, I'm trying to find it because I, of course, did not prepare very well for this. Okay, oh, there we are. I'm in the vicinity of the time it happened. Okay, well, I look. So basically, one of the main ones, the ones every fucking body knows, is F equals M1 M2 by R2, right? That's like the most basic one that I think you guys were talking about.
Um, you talking about Newton's gravitational law?
Yes.
Okay, yeah. More or less, I mean, that's where a lot of the discussion revolved around, yes.
So I guess my first question is hang on. You know what? You know what? I think everyone should hear what we're talking about first, right?
Absolutely.
Yeah. Okay, so this is going to be probably about it only lasts about 30 seconds because, like, again, he doesn't say different. He just says it over and over again. So playing this whole situation that lasted, for me at least, lasted an hour is unnecessary. So let me go ahead and get to share screen.
Welcome back. I'm not sure. It's some sort of automatic gain compensation, probably.
That's why there's a lag time and it seems to slosh around and it's not direct.
Haven't been able to hear me this whole time. All right, people. Sorry about that. I've been muted this whole time, so they have no idea what the fuck is going on. Computer issues. Sorry about being muted. I know you're seeing the screen, but everything is good now. I'm just trying to get everything back on the screen so you guys can see what the fuck I'm doing. Okay, here we go. I'm kind of happy it happened very early in the stream, so I don't have to be frustrated. There we go. Oh wow, why are my settings all fucked up? That is very... Oh, I know why. Da-da. I use the pop-outs. There we go. I apologize, Toro. Okay, we're good to go now. That was just...
No worries. It's okay.
This is constant chaos every time I do this. What was I doing? I was going to share this. Okay, I don't remember what was on that screen, but it doesn't matter right now. I'll put this over there. Okay. It doesn't look like much at the moment, people. But what's important here is the audio. So let me push play, or let me find this again.
Everyone, and then you have density, buoyancy, and viscosity doing the Gaussian surface being vector being caused by the... That's pretty close to velocity equals 0.
You're using
got height
gravity.
equals 1/2
Hey,
acceleration.
Samantha, fucking wait.
1/2 acceleration times squared. To simplify it, you got A equals 2 times height over time squared. Let's say drop a ball from 10 meters. It takes 1.43 seconds to fall. You got A equals 2 times 10 over 1.43 squared, giving it roughly what, 20 over 2.0449, giving it A equals 9.78 meters per second, right? So that's pretty close to deriving it on the spot. No big G required. If you want to get into the causality of big G, we have, of course, our better argument for electrostatic downward gradients causing the non-zero vector, right? Vector, of course, meaning it has to have a magnitude and direction. The vector being caused by the voltage gradient present on the Earth from the two different states of our charge distribution hemisphere called, Gaussian surface being the firmament, and our positively charged Earth. Sorry, negatively charged Earth in your world, right? Negatively charged Earth, positively charged top. Charge and discharge, whatever the two states are seeking equilibrium, those two opposing surfaces creating the voltage gradient, expertly creating the downward voltage gradient that would determine the general direction of down for everyone. And then you have density, buoyancy, and viscosity doing the general work of what you have previously attributed to big G. How are we doing so far?
I think that's about the saddest attempt to sound intelligent.
Yeah.
All right, so you heard it. Okay, so
Yep.
it's that the second I heard that, that was the first 2 minutes that I got there. I got there, heard him hit record, and he was already in it. Before we break it down, what he said, did it mean anything?
It meant that he knows how to do a little bit of mathematical sophistry, but doesn't actually explain anything at all.
Okay, and then that's when we got to this situation. So I heard that, and instantly I can't follow it, and this is what I think. I think Shane wants that to happen, because
Yep.
I have, because what we have on the panel right now between me and you is this is like perfect for this situation, because this is what happens. Shane goes on that diatribe, and he says a whole fucking lot, and this is what he's doing. He's doing it on purpose to affect me and Totoro for different reasons. He expects me and understand this. I have what you would consider a very basic understanding. I have enough of an understanding that I can have a conversation about, general relativity, forces, physics. I can have a conversation. I can go back and forth. I can't keep up with Totoro here, but I can have a basic layman's conversation that, or I think above layman is a better way of saying it, because I'm in these forums and everything. But Totoro here is extremely fucking smart. Like, if we were to break these things down, fuck, don't, you're so full of shit.
Compared to a lot of people, I'm basically a dumb baboon.
Yeah, well, compared to the people in all of these forums, congratulations, you're Feynman. But what happens? What was that? Okay. But what ends up happening is you are trying to break down everything he said in that whole time, but you can't because he won't let you.
Pretty much, yeah.
So what ends up happening is the smartest people that understand this enough to explain it are now having to sort out what I have now coined vector salad. And I say vector salad for this reason. And this is kind of going to go deeper into this conversation about it because it's weird. You would agree that there are ways to explain these things honestly, and there are ways to just explain it to get through it.
Yes.
I have. This is one of those topics where I know enough, but I don't know enough to stop the in between bullshit. So what I want to do. Okay, you want to share something?
No, it's okay.
Sure.
When we're ready, I've got my tablet up here, and we can scribble and talk about stuff.
Oh, perfect. Perfect. Because this is God, you are one of the smartest ones. Okay, so when I'm thinking of gravity, and this is actually a conversation I had the other night, so this is kind of, I'm going to have questions as well. I'm a very questiony person, if you haven't noticed. When I think of gravity, and I think as a vector, what I would do is I acknowledge that there's a force involved, a force affecting my object, and I would draw an arrow pointing down, right? That would represent the vector, the force vector that we're describing. Am I wrong so far?
No, I guess it's sort of yeah, it kind of makes sense.
I'm a layman. For a layman, that's right.
Sure.
Now, I have a question. This is off topic, but about the topic. Are there points in a vector?
Well, no, a vector is just a direction and magnitude. That's how it's defined.
Okay.
It's these two components, nothing else.
So if someone says, hang on, or going to your screen right now. So if someone says that a force vector has 2 points, they're full of shit, aren't they?
Force vector. Could that be interpreted as mean something?
Well,
No,
there is a force. There is a term called force vector.
Yeah. So the question is really, is Shane's entire charge, the thing that we asked him to do, is to produce a force law. And in physics, when you say that you're looking for a force law, what you're really looking for is, I'm looking for, and it's essentially whenever in physics you see the word law, what they actually mean is they expect you to produce an equation that predicts something, right? So they're going to be expecting a kind of some sort of an output that's going to depend on some inputs, and you get to define what this part is. So in the case of a force law, what we're asking you to do is, and this flat earthers generally will accept Newton's laws of motion, which one of the fundamental ones is F equals ma, right? So it's just the acceleration that an object feels is dependent, or rather the acceleration that an object feels is correlated to its mass and a force acting upon it. So that's essentially like Newton's first and second laws.
Yes.
summed into a mathematical representation. So an object that is in motion is going to stay in motion unless acted on by a force, and the force is essentially proportional to the mass and the acceleration, or you can basically rearrange it to whatever you want. So this is what we're looking for when we're looking for a force law. And in the case of gravity, like the actual real gravity, not talking Shane gravity, the force law is simply this. You can predict the force that an object will feel simply based upon the gravitational constant, and the force is going to be interacting between two masses. So the conventional model is that you imagine 2 point masses, and the forces between them. So I should call this one force mass m1, m2, and the force is going to be acting in between both of them equally, and it's going to be simply the product of the two masses and their separation squared in terms of distance. And here's the funny part.
Ooh. Okay,
You
I
can
have a
use
quick
this.
question. Hey, quick question.
Go
Quick
ahead.
question. Okay, because this is part. Okay, let me say something real quick. So, 2 nights ago, I went to this random server. I knew one of them, but I don't know these people. And I got on the panel, and they were talking about these vectors. And someone said, a vector. We were talking about how vectors have points, or blah 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 blah. But then we got into this equation, and I have and you're good at staying on track, so I can do this. We were talking about where the when two masses attract each other. So in this example, a person standing on Earth.
Right.
I was explained years ago by my guru Barney. Throughout there, Barney, what's up, sir? That in fact, the gravitational influence that we feel is not to the center, but it is the whole mass that is affecting you. It's a very weird calculation, but the sides of Earth do affect you, but not as much as down the center. But the bottom of Earth, the South Pole, if you're standing at the North Pole, the gravitational pull you feel isn't from the center of Earth. It is all of Earth that you are standing on. Am I wrong in that? Okay, perfect.
No, that's correct. That's correct.
Yes, okay.
Crucially, the force law that Newton gives is for point masses, so their shape is indeterminate, and they're perfectly point-like, so they have no size. So there's no actual, dimension to them. That's kind of by def.
Yeah, there's no diameter, no radius, no nothing.
Yeah, it's there to allow you to ignore shape effects, because that would actually affect. That's one of the reasons why, if you just do a naive prediction with the force law and centrifugal force on the Earth, you're going to get a slightly incorrect gravitational acceleration on the Earth, because the shape effects of Earth are such that it is not perfectly spherical, and so the shape does come a little bit. If you're looking basically at like the third significant digit, so you're down into the individual fractions of a percentage point of effects, that's where the shape effect can come into play. If you're just looking for the overall gross number, you can get that just from the force law and centrifugal force.
Now I'm going to ask you a question, and this question is going to be, I'm going to let you know, this is going to be my gotcha when I go back to those fuckers that were talking shit, because these guys were assholes. So R2, that measurement, that descriptor.
R squared.
Yeah. R squared, I'm sorry. R squared, sorry. That isn't to the center of the objects. That is to the objects then.
No, it's to the center of mass.
Okay, but wouldn't that be shape dependent?
That let me put it like this: this equation is accurate if the separation is such that the dimensions, the size of the objects, is essentially negligible compared to the distance. So
going to the center of the object isn't in saying that is where the influence is from. It's just giving it a description point, a reference point. I'm sorry.
Yes. It allows you to, as long as the size of the object is such that you can like the distance is significantly larger than the size of the objects, then this will be quite accurate. If you want to have if you're looking for a case where you have a very large object, so let's say the Earth, and you standing up on it, this equation will be quite close, but it will differ by about 1 percentage point, give or take, from a
Where?
naive solution. Because in actual fact, if you wanted to get the exact solution, or much more accurate solution, better than 1% accuracy, you actually have to do a 3-space integral. So basically, you have to, for each of the points of the Earth, you kind of have to sum them individually.
Yeah. And
And
that
that
was
gets
the
a
that
little
was
bit,
and that was
yeah.
referencing the sides of the Earth affect you, but right. That's
Yes,
just
and
the,
so the intuitive way to look at this, the intuitive way to look at this is if you think about, think about this guy here standing, and there's two cases, or we can basically model this as two situations. I have here a single ball of mass m, right? And it has a center of mass here, and I'm basically measuring the gravitational effect or the gravitational force. And in this case, on the guy here, the gravitational force is going to be just that kind of a vector directly towards the barycenter of the object, for simplicity's sake, right? But imagine that I take a model of the same situation like this. Instead of him standing instead of the mass being basically concentrated into a single spot, imagine I make it like this. And I have a mass m here, or mass m half. So I basically just split this thing up and separated them out spatially, right? So it's like two hemispheres. If you take these two objects together as a system, their center of mass is still here, where it was, right? But I have massively changed the distance between them, and I've also changed the direction of the force vector, so that now this guy in this direction feels only a tiny proportion of this vector, and a much bigger proportion of the vector is basically like laterally, but the two lateral portions cancel each other out, so you're just left with a teeny tiny effect down here. This is an extreme case of where the shape effect would take hold. Make sense?
oh, okay. Yes.
And so for the general solution, if you want to do this correctly, you would have to have some sort of description of the shape of the object. So it's going to be some equation of something, and then you do an integration. So you basically like break this object up into teeny tiny pieces, and for each of them you solve this equation sort of individually. And then whenever you see somebody say integral, or they write this kind of S symbol, what they mean is basically we sum them all up, right? So we take all the teeny tiny contributions, sum them all up, and we come up with an answer here. And that's going to be the actual force that you're going to feel in like the net resultant force. And there's a way to do these integrations in a manner where you don't have to do it like step by step. There's actually a way in mathematics, we call it an analytical solution. So if you kind of come up with a way to represent like the individual parts, but you write it as a single equation where the effect of this shape is all taken into account into the formulation on the right-hand side. So the entire effect basically is resolved in a single equation. That's what shape effect is. And in practicality on Earth, so if I go ahead and get rid of all of this, in practicality on the Earth, if you do that, you get, if you want to go, we're talking, just to be clear, we're talking in the individual percentage difference from just a naive solution here. In practicality on the Earth, what that will manifest as is some sort of a correction factor here, depending upon, some latitude, longitude, coordinates, whatever, elevation, something, right? So there'll be a tiny correction factor applied here to get the shape effect correct. Make sense?
Yes.
But for our purposes, really, the discussion with Shane was not at all about, like, we're not talking about the last 1% at the end. Like we're not looking to resolve this little bit here. We're looking to resolve this bit here. That's the question.
Yeah.
That's the one they don't even have an answer for. I'm
And
willing
that's
to grant them
and
this. I'm just gonna say like, okay, whatever. It's some detail at the end. We're gonna discuss that when it's pertinent. They haven't even solved this part. And the charge that we had for Shane yesterday, or at least the one I was trying to get him to, is there's an effect on Earth that we observe that everywhere, whenever you have an object, so it can be a little. It can be. You there?
Yep, I'm here.
Okay, yeah, you've turned off your screen share. Okay. If I
Oh,
have a
yeah.
basketball.
But yeah,
If I
my bit rate is going ape shit right now. So,
Gotcha.
yeah, I did fix something. Go ahead. We're here, still here.
Sure. So if I have a test mass, I have a basketball, a person, or a feather, and if I drop them, and let's say that I can drop them inside of a vacuum chamber, for the guy it might be a little bit uncomfortable, but if I can drop them all in a vacuum chamber, irrespective of their mass, they will all experience the exact same acceleration, independent of their mass, their electric charge, their whatever. And that number is always going to be very, very close to 9.8 meters per second squared.
Yeah, it's not an exact,
again,
but it's
yeah,
always in that.
Again, it slightly varies around the Earth because of various effects, but as long as they can get to within a ballpark this, they can. I'm happy. And so Shane's charge yesterday was to derive this number, but crucially, he has to derive it from his force law. It doesn't have to be well, it shouldn't be the gravitational force law, right? It shouldn't be this. It should be something else. So he should have a force law that's.
Oh, it should be hang on.
Yes,
it should be like V or whatever the fuck it is.
It should be. He should say that there's a force law that basically governs the falling down part. So let's call it a kind of a gravitational effect, but let's call it Shane effect.
Okay.
And there's going to be some electric terms, probably some magnetic terms, probably some density effect, some, I don't know, some viscosity, some Reynolds numbers probably, or whatever. And at the end here, and so this should predict the force law. And from that, he should then be able to produce outcome a gravitational acceleration. Once I take all of this crap into account and plop it in here, I should come up here with an answer that says, at the end of the day, 9.8 meters per second squared. For gravity, I can do the derivation very easily.
Yeah.
For gravitation, for like Newtonian gravitation, if you want me to do that.
Yeah.
It's a very simple derivation. We start with this. So this is the general force law. And we're going to say that every object that falls is under the influence of some sort of force that's pulling it down. And I'm going to postulate that this is the force that pulls it down. So I can basically take these two sides and put them equal. So I'm going to say mass of the object times an acceleration is equal to gravitational constant, mass of the Earth, times the mass of the object, so little m, divided by the mean radius of the Earth squared. So basically how far you are from the barycenter. Now what you'll notice is that these m's over here are the same.
Stop, hang on. One second. Okay. I think I just clarified where I was confused, but correct now. That center of mass isn't the center of mass. It is just where those two objects' barycenter is.
Yes.
It's where. Okay. So when physics, when you're talking about this, you're not actually talking about the center. So that means basically what I mean is when I'm standing on Earth, I can't use that barycenter as my reference. Which is why in the equation it is the center. But when I say that the gravitational influence that affects me isn't at the center, it's the whole mass. That's why it's not the same thing.
For practicality reasons, we can basically treat it the same because the mass of the Earth is so massive compared to your average human that your effect on the distortion of where the barycenter of the system is essentially negligible. Like
so therefore, when I'm standing on Earth, that equation should not apply for the conversation.
It does. No, it does. By and large, it does.
But it'd be off, though, remember? You said it wouldn't be so accurate.
It would be to within a single percentage point of the actual answer.
Okay, so then where does... Okay, so if I'm standing on Earth... See, now I'm confused again. If I'm standing on Earth,
right?
I'm correct in saying that the gravitational influence is down because
Yes.
of the mass that's under me,
Yes.
right? Okay. Is this correct? Because this is now the other side, and I need to understand it. The gravitational influence is to the center of Earth.
Yes.
Okay. To me, you have double spoke. To me, you said yes to both, and to me, they're different.
It's the thing is that the center of mass of the system of Earth and Sean is essentially still the Earth, because the Earth, you weigh on the order of 10 to the, let's say, second kilograms, right? So you weigh, and we're talking essentially like ballpark numbers. So 10 to the second kilograms is about 100 kilograms, give or take. That's your average human mass. The Earth is of order 10 to the 24 kilograms. So there's a 22 orders of magnitude difference. So the amount of displacement of the Earth-Sean barycenter towards you caused by your mass is essentially nothing. You can basically ignore it.
So then
Make sense?
referencing, no, yes, but no. I'm trying to figure out how say okay that when referencing the center of Earth, wouldn't the only thing you could say is that the vector direction is towards the center, but it's not to the center.
It largely is. That's the net result. Like if you want to, let's say you break up the Earth into 1,000 little pieces, right?
Mm-hmm.
And for each of them, you do a solution individually. Make sense?
Of what it affects me.
Yes.
Okay.
Because you have a gravitational exchange or an effect with each atom.
I am so confused at the moment. Is that an internet issue?
A couple of kilometers, really, in actual fact, because the Earth is very close to being a perfect sphere, but not quite, and it is not perfectly uniform in mass distribution. That is why I say, when we're looking for correlation to within, about a percentage point, then we can basically ignore all these details and just treat Earth as a perfect sphere of uniform density and just be done with it. Make sense?
Okay. Yes. Yeah. Absolutely. That does make sense.
Yeah. Again, there are gravitational studies that will have to quantify this, because we have gravimeters that are extremely sensitive. When we're talking about the sensitivity of these gravimeters, the typical way you measure the force of gravity on Earth is you basically measure G very, very accurately. And the unit typically used in those studies is called a gal, which is a 1 centimeter per second squared, or 0.01 meters per second squared. So since we have 9.8-ish, right, meters per second, so there's about 9,800 gals is the standard acceleration of gravity. And these gravimeters are sensitive not to 1 gal, so I'm going to write it like this. They're not sensitive to 1 gal. They're sensitive to basically down in the micro gal region. So they are sensitive to like variations of less than like 10 to the minus 8. So like 0.000001%. That's how sensitive they are. So when you're talking about sensitivities down there, even a single cloud or a storm cloud being present above your meter might affect it.
So this is like weighing an apple on a truck scale.
Yeah, probably a lot closer, a lot more detail than that. A lot more like a
but
truck.
Just in a sense that this method gives you
right.
more details.
Imagine it's like your typical truck, an 18-wheeler, one load, it's going to weigh about 40,000 kilograms, give or take. So it's about 80,000 pounds. Mm-hmm. You're talking about measuring it down to the like
Does it have?
milligram levels.
Yeah, you can measure. You're going. I want to know if someone
Actually,
took off the valve
microgram.
cover on the tire.
Pretty much, yes. Probably down to like the microgram levels is how precisely we could measure it. If you're talking about like if you want to have the sort of scale comparison. So yeah, literally, the difference between a mosquito sitting down on the truck landing on it and taking off.
That's badass.
So that's the limit of the precision of these instruments. But when you're talking about that level of precision, then yes, you have to take into account, here's your meter on some sort of a calibrated spring or whatever. And then you have to take into account whether there is a storm above you. Because the mass of this water, and there's a non-trivial amount of mass, there's like megatons of water, so millions of tons of water there, that will give enough of a gravitational upward pull that it will screw up your measurement downwards.
So that means where the moon is matters too.
Yes, absolutely. Very much so. Even the sun.
Yes.
So
Wow.
they will need to, they'll need to, they will need to actually check for that. Actually, let me turn off Wi-Fi here.
So that's like a situation where you wouldn't go out and start measuring, like you can, but if you're looking for a specific reading of something, you may only have 5-6 windows a year.
No. I mean, no. I mean, as long as you can quantify the errors and the effects, then you're good to go. So you can measure it.
Okay.
Yeah, when you have a look at these gravimeters,
Wait. This is okay. So this was actually a big test. Actually, hang on. So they actually did this, and correct me if I'm wrong. They did this during the eclipse, and or not this eclipse, a eclipse, and it was like fuck, who did it? It was a big science thing. It was. Fuck, what was
I suppose. I mean, what you'll
I think
find
it was,
is, for example,
I think it was around the same time during the Einstein days when they figured out general relativity was correct or whatever. I think it was part of another test they did.
Oh, you're talking about the measurement of the distortion of light due to gravity.
Yes.
That's how they initially confirmed general relativity. That was the first practical test. Yes.
Yes.
What I'm talking about here is a direct measurement of gravitational acceleration, which is somewhat independent of that. Anyway, to come back to what I was talking about, like this is the general derivation of the acceleration on Earth is basically just gravitational constant times mass of the Earth divided by the radius squared. However, there is a slight complication here in that there is a centrifugal element, right? So we say that the Earth is spinning about its axis. So you have to tell me basically to be able to, first of all, even quantify the centrifugal force that you're going to be feeling, because you're measuring the acceleration inside of a rotating frame. So that means you have a fictitious force that's kind of like pulling you out, and that's going to reduce this measurement. And let's see,
wait. But wouldn't
omega r squared or something?
But wouldn't Earth's rotation, and this is I kind of just got confused. But wouldn't the machine be calibrated to zero? No, because it's in a different direction. Never mind. If it was one direction, you could calibrate this apparatus. But
so
it's
here
not
I'm not
one
actually
direction.
I'm not actually talking about a specific experiment. What I'm talking about is how we can make a prediction. That's the thing about. So I want to basically expose the way that Shane did it, or Shane basically circumvented the charge. Is that he was charged with producing essentially this, and the thing is, if you take our known gravitational constants, which G is 6.6 times 10 to the negative 11, I think. I have to check. And the mass of the Earth is about 5.9 times 10 to the 24. Radius of the Earth is 6371000 meters. If you plug all of that into a equation, and I'm going to do that just quickly here on my computer. Let's hope I got the numbers correct. I'm going to check. 5.9 times 10 to the power of 24 divided by 6371000 squared. And you're going to come up, hang on, I got 6.67 is I think the gravitational constant. Let me see.
And the gravitational and the gravitational constant is just what is always felt.
I can actually talk a little bit about how we figure these things out. Mass of Earth is 5.972. So if we want to get down to like the last, okay, so if we go 6.74, 6.674 and 5.972, and if you plug all of that in, I can just quickly give you the answer out of the calculator. It's going to give you an answer of 9.8195 whatever meters per second squared. And you can actually work out the exact units because this is kilograms. This is what's the standard.
Hang on. So what you just did right now is all you're asking Shane to do. The difference would be the only difference would be go back down. The only difference would be is your G, your constant. You want to know what his constant is.
No, not necessarily. So in his case, he says that this is fictitious, doesn't really exist, whatever. So I'm expecting him to produce...
I thought he said gravity. He said that equation does work. He said that is real. He says he.
Well, in that case, that would actually imply a spherical Earth. So that'd be a bit of a problem for him.
That's what I'm fucking saying right now. Like,
because then to actually arrive at the number here, you have to use the mass of the Earth and the radius of the Earth, which.
Okay, so
I'm sorry.
So last night, I'm pretty sure you may remember me saying this. I said this a lot.
Yes.
I was saying, Shane, are you saying that you're encompassing everything? Because he wasn't saying gravity isn't real. Matter of fact, I heard him say, I'm pretty sure I have it recorded, him saying gravity was real.
He does say that the effect of stuff falling down is real. Yes.
Yes.
Whitsitt says that. Jaron says that. Everybody says that. That's not a question. The question here is...
They said it was... I think they say it's electric. Boogie, woogie, woogie.
Yes. And so what I'm asking them is to disregard this. That doesn't exist for them. They need to propose a new force law where if I plug in a test case like this, I need to be able to solve for G using whatever values and constants that they say are applicable here.
But wait.
Object.
Now this is what's confusing me now. Why do you keep saying they need to find G if G doesn't exist to them? What should G be?
But the G is just a name. I'm looking for explaining why the acceleration exists. So, as I said before, whenever we have a test and we drop something, it can be a person, can be a bowling ball, it can be
a lighter,
feather,
Yes.
Doesn't matter what it is. If we drop them, we always observe, and especially if we do a simultaneous drop, we always observe the same acceleration downwards. This number is the same for everybody. Why?
Everything. Okay.
And they need to be able to predict it. So if I take their force law,
hang on, go back down to the little thing. Okay. You said why. Okay. Let's do this. It's gonna be ridiculous, but let's do this anyway. I'm gonna say let's start with density. Why not density? Just give me I know this is ridiculous. Just give me the answer.
What I'm saying is.
No. Tell me why it can't be density.
Let me refine this. I'm not saying it can't be. I'm asking.
I'm saying it can't be.
That's okay. There's another experiment that we can do, by the way.
Yeah, but look. The three objects that you have in our hypothetical vacuum. Just in this, I can say their density is not the same. So density is not the reason for that acceleration.
That's okay. There are cases where, for example, their masses are very different. So this is going to have mass 1, mass 2, mass 3. Mm-hmm. So why do they all fall at the same rate? Why do they accelerate all at the same rate? And the reason is in gravity is that essentially the mass and the force are going to be essentially exactly balanced, and that's normal. That's okay to have a balancing effect to where an effect
A balance?
perfectly balances on both sides, and you end up with a constant number coming out the other end. So for
Okay,
example, if I do,
that confuses me. About what is the balance between
meaning
M1
meaning
and
they compensate. So if I
okay,
solve,
okay. The
right,
the reason
so,
the reason the Earth does not actually come up to our feet.
no, think of it like this. So here I have a scale, right, a weight scale that measures, essentially, it measures this force down that a basketball exerts on the scale versus a feather exerts on the scale. So these two forces are very different. So this is F2, this is F1. Basketball obviously is going to weigh a whole lot more.
I think the forces are
So,
the same.
right.
Oh no. Okay, I see. I ignore what I just said.
Yeah, this is going to read a very different number here than
Yeah,
here.
yeah.
So I'm asking them to produce any equation. I don't care what it is, but give me an equation that says if I can predict the force on the left here based on whatever gobbledygook I put here.
Wait a
And
minute.
you can
Wait.
and they can produce
Can't
any
you?
constants.
You can do this
It
with
can give
electromagnetic. But can't you do this with electromagnetic or a magnetic
yes,
or?
you can.
Okay, so
Yes.
then if they came up with that, what couldn't you?
Hang on.
They just.
I'm gonna explain. I'm gonna say, you can come up with constants. You can come up with independent properties of the object, like for instance, their intrinsic mass. So this is gonna have a different mass than this. You can come up with some separation from some surface. I don't know, let's call it an R value of something. You can come up with anything that comes in here. It's for them to define. They get free reign on the right-hand side. But once that's done, then that's what I'm basically saying here, is produce a force law that allows me to predict how much an object's going to weigh if I know it's whatever, whatever quantity you want. It can be the electric charge, it can be the, I don't
I
know,
see.
magnetic field
Okay.
strength, whatever. So
Okay.
allow
So
me to predict the
yeah,
weight
I see.
force of the object. And so
I see
from
what's
there,
happening. Yeah.
I should be able to take whatever you put in here, say equate it to F equals ma, and if I cancel out the mass of the object, I should then be left with the acceleration downwards, and this must be the same no matter what the mass of the object is, and it should come out to approximately 9.8 meters per second squared. Because this is what we observe experimentally. So this is where the
Yes.
experimental check is going to come.
I
But
see now what
you
you
have,
want. I see what you
yeah,
want now.
but you,
The problem is what you want is they're saying it's not gravity, it's something else. But
right.
so
So
what you're saying is okay. Well, if it's not the constant that's in every fucking equation that works, I need a constant that I need to see your constant that every time I use it in this situation, that situation, we still keep getting this 9.8 because Shane does agree 9.8 ish is the reality. That is the conclusion no matter what. So what tutorial here is saying is okay, cool, Shane. That means you're saying it's not what we are calling gravity. It is not that constant. And he's going correct. And you're going. So what you're saying is okay, perfect. Show me. Say, since we're taking that constant out of the equations, all the equations, what did you replace it with? And Shane's going, I don't need to show you that.
Yes. And so what he did actually, and he says that he derived it, but what he actually did was kind of reverse engineered it. Typically, the way we do this kind of stuff is first we propose a law. That's you had it already in the intro, Feynman's guess, right?
Yes, it's my favorite.
This is the guess. Then we make a prediction. And we actually also calculate this. So we take your law, we apply it to something, and we calculate a consequence. And this is what in Feynman's example is called, we compute. Then we compare to some, or rather we measure. Right, so we make some sort of an experiment that is going to compare these two, the measurement to the computation. Crucially, your computation can't depend, can't simply be the measurement reversed. And that's what Shane did. Shane said that the Downs acceleration is essentially the change in velocity over the change in time. And this is measured, this is measured. So what he said is that, well, if I drop a ball and I measure it has traveled some, distance over a time, then from that I can backwards work out the acceleration. But you've measured this, you've not predicted it. You can't use the actual experiment to compute your prediction for the experiment.
Yeah. Okay.
What I mean specifically.
So this is like the best one. It's like you're going. He has a ball in his left hand, and
Yes.
he go and you, and you go and the test is I'm gonna throw it up 10 feet in time. See how long it takes to get back to my right hand.
Yes.
And what he's doing is he's going. He throws it up and goes 1, 2, 3, 4. Catches it and he goes. The prediction is 5.
And then he just says, yeah, and I measured 5. Yeah, okay, cool.
Yeah.
You've just done the back and forth through this equation, and you haven't actually predicted anything. And what I was trying to impress, or was trying to say there in the chat, but it was kind of lost yesterday, is it's like trying to imagine you have a car, right? And you're going to say that the reason that the car accelerates is that it burns fuel with oxygen, right?
Yes.
And that's going to make it go. That's going to make it accelerate at some rate. And so I'm going to say, okay, derive the acceleration from some properties of the fuel and the oxygen, and give me some way to calculate it from the input. And instead, then what we're going to do is we're going to take some known amount of fuel, and we're going to measure how long it took the car to do a kind of displacement over some change in time, right? So that we're going to basically predict the acceleration from the causal factor, and then we're going to compare the output. What Shane did is the opposite. Is he went, okay, I'm saying that this is the
car
cause,
goes.
but I'm going to compute the acceleration from the final output measurement, and then I'm going to say, hey, look, it agrees.
So basically, what he's doing is he's going. The car weighs this. It's going this fast. I found it. I predicted the acceleration.
Yes, and that's kind of stupid because then he didn't actually establish this causal link. This is not confirmed because it could be. Who knows? I mean, the car might as well have been, electric. Might have been falling down an incline, whatever.
Now, hang on. Now, erase the road and half the car.
Half the car.
Half the car.
It's gotta be.
Yeah, that's fine right there. Yeah, perfect. Okay, that is what Shane is giving us. We don't know what the surface is. We don't know what the situation is. We don't even know what kind of car it is. But he's going. Well, this is the answer.
He's not proved this link, because this is what we're trying to. Yeah,
but
that's what we're trying to get him to.
Yeah, but because we don't have sufficient data, surface, car.
Yeah.
Length,
actually,
we can't get to that.
It's okay. I mean, it's okay if he doesn't give us some parameters. He just has to give us enough information to where he says that this is the cause and this is the effect, right? So we have to be able to take the cause, predict the effect, and then we have to be able to measure some independent variables.
Okay, hang on. Now stop. Hang on, stop real quick. Okay, I'm going to ask you this, and I want you to just give me this blanket answer real quick. Okay, this is us doing this right now. What we believe in. Tell me what the cause is.
For what? For the acceleration of a vehicle?
So I'm talking to Shane, and we're talking about you. And Shane says, I want to know the cause. You say to him.
For what? For gravity or for the vehicle accelerating here?
Yes, for this situation that we're looking at. You said, because you said in this situation that we're looking at.
You're trying to look for what this would look like.
Yes.
So I would formulate that the fuel has a certain energy content.
Okay.
Has a certain amount of joules to it. Then I'm going to say that. I'm going to say that the vehicle accelerating here is going to for combustion, after combustion, fuel plus oxygen, that's going to release that energy. And this is actually fuel plus oxygen. That's got some sort of chemical reaction that's going to happen. That's the energy. Then I'm going to correlate that the car at the end of the acceleration period is going to have some kinetic energy that's going to be 1/2 mass of the vehicle times the velocity squared. And crucially, I've said that the energy here is some sort of fuel plus oxidizer plus multiplied by, there's probably going to be some correction factor to the drivetrain efficiency. And from there, I'm able to establish that, okay, so if I say to somebody, hey, you wanna accelerate a car from standstill to some velocity, and so in order to do that, you basically take the mass of the car, and you can actually just obtain the values of the amount of fuel. So X kilograms of fuel and oxygen is how much you're going to need, and then you just take a car with the requisite properties, feed that in, run it, and compare the velocity at the end versus, it's going to be 0. Velocity 0 is going to be 0, and you're going to compare it to my prediction, right? So I predicted that it's going to say output some velocity there. Let's make it like a little bit clearer, because it's getting a little bit confusing. So I say that there's some drivetrain efficiency, some fuel plus oxygen. This is going to be the energy of the fuel, and it's going to be 1/2 mv squared. That's kinetic energy. And so what I'm going to say that ultimately at the end of the acceleration, what you're going to have, so this one's going to go up here, so it's going to be 2k. I'm going to basically just solve for the velocity at the end, and we're going to take the square root of this. And so I'm going to say that if you want to know what the speed of the vehicle at the end of your acceleration is, take the energy content of the fuel once combusted, multiplied by twice the 2 and the coefficient of drivetrain efficiency divided by the mass of the vehicle. And so what you can do is say, I'm going to take a vehicle that weighs 1,000 kilograms. I'm going to take fuel plus oxidizer that has an energy content of, let's say, 1 megajoule, and a drivetrain efficiency that is something like, I don't know, 80%, 0.8. And from that, I should be able to derive what the speed of the vehicle is going to be at the end of the acceleration. Make sense?
Okay, so yes, actually it did.
And that I can then I can independently measure the output, the predicted velocity versus the actual velocity of the vehicle.
Okay, so and so this is exactly why I just asked you that. What I was getting from last night is that Shane was repeatedly asking for this first. Am I wrong so far?
No. Whenever I charged him to produce the force law for his replacement for gravity, he gish galloped and basically tried to do a bunch of burden shifting to say that, well, I'm not going to produce it unless you can produce yours.
You produce it, and so you just produced it, right?
I mean, this is the acceleration derivation for gravity. Yes, that's what it is. It's literally just 2 steps. But he says that that's not a thing, or rather, I'm willing to entertain to basically entertain this idea that this doesn't work, and I'm going to say, okay, it doesn't work. Forget this. This doesn't exist.
Yep.
Give me yours.
This is yeah.
Give me yours.
So that right there. Hang on, stay right there, because I'm taking screenshots. So that right there, what you just showed, is what you want to show you want to see his final conclusion. You want to show him to show you what you just showed us.
Yes, I would expect him to be able to produce a force law for his replacement for gravity, or whatever effect he says that it is. Because he makes a bunch of claims. I mean, if he said that I don't know what it is, then I would say, okay, you have no force law, you've nothing there. There's no there, right? So he's just saying it's not this. So he's saying it's not this, but he doesn't know what it is.
Yeah.
If that was the case, we'd be fine. But he does say what it is. He says that it is the electromagnetic force, or some electromagnetic effect. He says it's the effects of density. It's the effects of a buoyant force. And he says that it's also related to viscosity. So I don't know, like Reynolds number might factor into it or whatever, something.
Yeah.
Probably
So
a
hang on.
surface
Now, hang on.
effect.
Now, hang on. So I'm going to ask you a question. So with all the ones those four you just listed, you can start at the beginning of this equation trying to figure this out. I'm assuming that somewhere in all the shit you did, if you were to replace it with electromagnetic, it would
Right.
you would hit
It
a brick
falls
wall.
apart. It wouldn't work. It
And
wouldn't work for
yes,
a very simple
okay.
reason, or for a bunch of reasons. Why
No,
we know gravity is not.
hang on. Before you say the reasons, that would be the reason you want Shane to do what you did at the bottom of this. The equation
Yes.
that everything you just did at the bottom, go down all the way down, go all the way to the bottom.
Okay.
Right. Keep going to the car. Your whole down,
Yeah, okay.
down. Right there, right there. You want Shane to do this because you know that if you where is it? It would be KF blah 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 blah. The top.
Okay, yeah,
left.
this K
Yeah,
fuel
yep.
plus
Yes.
oxidizer is some
Yeah, that's
energy.
with electric magnetic. That's where your brick wall hits, right?
He would start hitting contradictions. Basically, that's my contention.
Yes. Yeah.
Um,
Okay. Perfect.
So
That's-
one of the fundamental properties of electromagnetism is. So here's the reasons why none of the explanations that he proposed work.
Okay. So now So now what you're doing is okay, and
I'm trying to
this
debunk him at this point.
No. What you're doing is you're going to do what you asked him to do using the things he keeps saying he would use.
Yes.
Thank you.
Yes.
Perfect.
So he has a bunch of papers mentioned and stuff. And he says that there is, and this is quite correct, in that there is an analogous kind of sort of electromagnetic force law.
Can you put EM at the top of this?
And we can say FEM, right?
Well, but
Some
I want to make it. I want this to be like a title part. So, because I want you to
Okay,
understand.
let me-
What I'm going to clip this, like what we just did.
Okay.
Show him screenshots, and I'm gonna show him this stuff because this what I want him to understand that what he's asking for is doable.
No, he already knows this. I'm just reiterating his point. He says, so this is the Coulomb's law for point charges. So if you have 2 point charges, each of them has a charge Q1, Q2. They are separated by a distance R, and K is essentially the vacuum permittivity and permeability constants all rolled into one number to make it. It's essentially the scaling part, the thing that gives you the correct units at the end in size compared to the input charges. So
the data.
This is quite analogous if you compare it to gravity, where g is the gravitational constant, mass 1, mass 2, divided by the distance squared. So all of these terms look very similar. Here's the problem. Q, these are the electric charge.
Yes.
Is both positive and negative.
Yes.
So what I can do is if I make a positive and a negative charge here, they'll attract. So let's go like this. They'll do this.
Positive.
But if I make 2 positive charges, then the force is opposite. Or if I make 2 negative charges, the force is also. Yeah. So they'll push away from each other. Gravity doesn't do that. There's only one type of charge for gravity, and it's always always I would say positive in the sense that it always attracts. So this is essentially a kind of minus here at the start. It's always sucking towards each other. There is no negative gravity.
So in a sense so if he's using electromagnetic, he would have to show the repellent force as well.
He would have exactly. That's one part. Second of all, one of the issues here is that mass is an intrinsic invariant property, at least the rest mass. So if I have a bowling ball, it's typically you call it rest mass or just mass, sometimes called M0. Its rest mass is an invariant property as long as you don't like try and mess with the ball itself, like trying to break it apart or explode it or whatever. its mass is an invariant, but it doesn't matter if you add more mass, by the way. So if you take another bowling ball here, you don't suddenly change this mass. All you just did is just add another m0. So now you have two m0s. Make sense?
Yes. Yeah.
But with a point charge is if I have an electron here, which is negative, and I take a proton or a positron, whatever, I add them together, what's the resultant charge?
0.
Exactly. So if I use this as a force law for downwards acceleration, all objects should float, because one of the fundamental principles of atomic chemistry is that atoms have a net charge of 0, because there's a negative electron, a positive proton, the two are in balance, therefore atoms are electrically neutral. Therefore, basically most lumps of matter, if you take a potato, its net charge is going to be 0. And you can actually
Now,
help it out. Sometimes you can build up surface charge. You can actually help it out by grounding the experiment.
okay,
So then
so
charge builds up, goes
now
away, and then
I want
then
I
this
want to
would
say,
say
I
it
want
should
to make
float.
something clear though. Yeah, I want to make something clear. So this is possible. This is not
Yes.
BS. Now
Yeah, no,
here's the
absolutely.
problem. No, yeah.
Coulomb's law.
Yeah. Here's the problem because it just clicked because I've literally had this conversation with Witsit and he won't answer it. Here's the problem. What he's saying is that things can float, and this is doable. The problem is this: for a balloon to rise, for a person this is better. A person to jump, the the amount of charge that a human would have to create to leave the surface of Earth is not logical. It's zap you and fry you, and you would just disappear. You wouldn't exist anymore at all. For that, for you to, and this, hang on, and this is for you to jump.
Yes, in order to generate, so 100 kilograms is about 1 kilonewton of force on Earth. So that's about the amount of force that you'd have to generate by way of an electric field. Mm-hmm. In very simple terms, there's actually a way to, this trivial force law here is a little bit, it's for point charges. There is a more generic form which takes the electric field strength and multiplies it by the charge. And that's also going to give you essentially the force. And this is a vector field. But the idea here is that, first of all, you'd have to have either an enormous amount of charge built up, or the electric field would have to be so incredibly strong that you would essentially have lightning just penetrating through the air, just because of the fact that if the intensity of the electric field, you'd have any charge like up in the ceiling would suddenly start discharging into the ground or whatever. Make sense? Because,
yes.
Yeah, the field strength is so powerful, or the other way around. The field strength is so powerful that you would essentially end up with really weird shit happening all the time. And that is how Witsit did it with his Van der Graaf generator, by the way. So what Witsit did is he essentially took a Van der Graaf generator that generates an electric field potential here of about 100,000 volts, and he put a bunch of styrofoam, which is electrically non-conductive, and generated an electric field potential of not 100 volts per meter. They say that it's 100 volts per meter. Witsit probably generated well in excess of 1 million volts per meter, because it's like 100 kilovolts over a distance of like 10 centimeters.
Mm-hmm.
And all he was able to do is get some very lightweight, electrically non-conductive styrofoam to build up enough charge
to move
to where he was able to lift it. Here's a very simple way to fix this. Use a conductive material. So make this. Yeah, he said I had iron filings, whatever. Okay, well, in that case, how about you just take a little ball and attach a wire and ground that wire. So just hit that into the ground.
0.
And then
instantly.
Any charge buildup is immediately going to run off into the ground, and you're going to get no effect. So, even though you've generated a field that is
Now,
10,000 times more powerful
yeah.
that you claim generates the very massive and very obvious downward stuff falling on the Earth.
Now make that whatever the fuck it was with whatever object he said he used. Make that a person.
Yes, you'd kill him.
Yeah. Again, this is a weird situation because here's the problem. You're on the ground, right? You're standing on the ground. So that means not only do you need the million volts?
Yeah, million volts per meter, probably more than that.
Yeah. Okay. So once you use that, you have to use more actually.
Probably
To
a lot
jump.
more. Yes.
To jump.
To levitate the guy, or to get him to, you've essentially like to negate the gravitational effect, right?
No, because hang on. The problem with that is the first issue is you have to be able to null the effect.
Yes, and once you've nulled the effect of stuff falling down, then it would start to float. But the trick is that in order to do that, you have to generate such a tremendous field to where, by the way, there is actually a kind of well-known constant, essentially, or it's not constant, it's more like a rule of thumb, which says that the resistance of air to arc forming is about 10,000 volts per centimeter. So if you have a plate that is two conductive plates that are 1 centimeter apart, so it's about a third of an inch apart, then if you have a field potential of 10 kilovolts or 10,000 volts, you're going to start getting arcs across it because the electric field is going to start essentially trying to neutralize itself. You're going to get charges jumping through the air.
Time out. This also means this means that, like, if this were the case, when you're walking down the street and it was like a very humid, cloudy, like a thunderstormy day, at will, you'd be able to shoot fucking lightning bolts at your fingers at shit.
Perhaps. I mean, the thing is more like if you try to levitate a person with a voltage gradient greater than, like, I don't know, million volts per meter, probably a lot more than that, then before the guy lifted off from the ground, he would basically start throwing arcs into the ceiling of the lab off of his head.
Yeah.
And that is generally not very good for people.
And
he can't.
You know what instantly comes? What instantly comes to mind is fucking what's his name? Was it Tesla? No, it wasn't Tesla.
Tesla?
It was the elephant.
Edison, the guy who electrocuted elephants.
Yeah. I imagine that when I see.
You'd
like that is what I imagine.
The guy,
Yeah, I imagine that when I think when Whitsitt goes, okay, fuck it, I'm gonna show them.
Yes, he would cook the guy.
Yeah, exactly. This is just ridiculous.
So he wouldn't have lifted off. He would still probably need a lot more than that.
Yeah, again, he need a light. Every time we hear about someone getting hit with lightning, the story would go, Bob got hit by lightning. Motherfucker floated up to 100 feet and just sat there for a little while, and then he just gradually fell back to earth.
Yeah, it's one of those things that never happens.
Ever. Well, I've seen it in some TV shows. It's pretty badass. TV
shows. I mean, if your reference for physics is the Avengers movies, then I mean, knock yourself out. But you're not really doing actual science.
It may be. Okay, so where we've gotten so far, and this is the best part about this. You've only talked about one thing on his it is because of list.
Yes.
Before he even got to the next three, they're already dead.
Yes. They're already dead. But so they work around this. They are actually, I think, aware of this problem. So they work around this by saying that the electric field is not the thing that derives the force, but rather it's the thing that sets, they call it the bias, so the direction of motion.
So now what they're saying, is that we are not affected by electricity.
What they're saying is that if you think of the like somebody standing on the ground, they're going to have a force, some sort of a force pulling them down. What they're saying is that the electric field sets the direction of this vector, but not its magnitude. Just kind of stupid, to be
Okay,
honest.
wait.
Mathematically.
If it doesn't express magnitude, then it's impossible to get to 9.8.
Yeah, well, not just by itself. So by itself, yes. But what they're then saying is that the force is derived from density, viscosity, and I don't know, like some force of buoyancy or something.
Which, okay, so
It's
hang
kind
on,
of
stop now.
stupid.
Hang on. Okay, so now we can move to the next one, density.
Yes.
I
Yes. Density.
don't think
That one's
we
even,
need.
That one's
I
even
don't think
dumber.
I don't think. I was just about to say. I don't think we need any equations. I don't need. We think we need any examples of why density makes zero sense.
I mean, we can make a simple test for it, right?
A vacuum chamber.
Yes. They postulate that density somehow sets the scale of the force. Okay, fine, no problem. We'll play with it. I'll make a vacuum chamber.
Wait, time out. There's no 9.8 in that then.
Hang on. Well, there might be. So that's why
For-
we're kind of.
for-
I'm not pre-assuming
for one thing-
that they're. Yeah, I'm not pre-assuming their result. I'm asking them to produce a prediction, and then inside of the vacuum chamber. And in order to avoid, and the reason why I'm putting it inside of a vacuum chamber is I'm trying to avoid any kind of aerodynamic effects, any effects of the air or whatever, right? So I'm basically just making sure that there's nothing in there other than the test articles, and to avoid any kind of surface effects or anything like that, I'm going to
Least
take
amount of
two
resistance.
I'm going to take two materials of exactly the same shape. So it's going to be two test cylinders of exactly the same shape. They're both going to be metals so that they're both electrically conductive. And I'm going to try and match as close as I can all of their magnetic and electric properties. So say, for instance, this guy here is made out of aluminum. This guy is made out of copper. Aluminum and copper do not weigh the same. Or even better, let's make this out of iron. Well, this guy's iron is ferromagnetic, so that might be something for them. In fact, I think lead might also be diamagnetic. So this is lead, this is aluminum. Exact same shape, exact same most everything, other than lead
The composition of
weighs. Yeah, lead weighs about 5 times as much in the same shape. So it's about 5 times more dense. So what I'm expecting then is that if the force pulling down in some ways depends upon density, therefore the acceleration should in some manner depend upon the density of the object. So I expect aluminum to fall down much more slowly than the lead. But that never happens. So clearly this creates a contradiction. You following?
Yes.
So that, by the way, if I use the same shape of test masses, I wouldn't even need a vacuum. I'm just putting the vacuum in there just to be a little bit more
protected.
insulated, more protected from criticism. But even if it wasn't a vacuum, the air would have the same density here as it would here, and because they're the same shape, any kind of aerodynamic effects of acceleration or something like that, viscosity, whatever, would have essentially the same effect on both of them. So that would null out.
Okay.
And by the way, in addition, I can even just put a little wire off to the side, off of them with enough slack, such that they are both electrically grounded to the experiment. So therefore, once they start falling, there's no electromagnetic force affecting. In fact, I can literally just take the entire test chamber and ground that.
Ground it.
Be done with it. So there's net charge of this thing is 0.
That's a big.
So what?
So what? Hang on. So what? The biggest thing they have to avoid, and what I'm seeing is they can't, is that zero, that net zero.
Yes.
Everything that they're saying so far, everything equates to a net zero. To be possible.
Pretty much. So there is. So what I'm saying here is that each of the effects that they're proposing, I can control for, I can exclude. Design an experiment that basically controls for it and makes sure that it has no effect on the experiment, and stuff still falls at exactly the same rate anyway. So that tells me that whatever this downward acceleration is not dependent upon density. is not dependent upon electromagnetism, is not dependent on any of the 4 or 5 whatever things that they're saying. But in order not to strawman them, I'm willing to say that it's something, but they have to give me something to work with so that I can make a prediction and I can design a test.
Yes, because so the importance. Yeah, hang on. King Crimson. Yeah, it's Shane St. Pierre. The conversation that we were talking about. I have to check with Demon Strike because I know he recorded. If he uploaded it, I'll share that link in the description. Otherwise, I have about 50 minutes of it. I haven't uploaded it yet. I'm going to find out how much Demon Stride has of it. Or, I'm sorry, he changed his name. Mr. Stride. I'm going to find out how much of the conversation from last night he has, and whoever has more, I'm going to share the link of it. It was about, it lasts about 45 minutes to an hour. The reason I wanted to do this is because Shane wouldn't give us time for this. Shane wouldn't give us time to break down what he said, and he sure as hell wasn't going to do what was being done. Because what's being done right now is what would have made us understand how he came to his conclusion. Shane's not willing to do this part. The reason I wanted to do this, I even asked Totoro last night about this, if he wanted to do this, is because Shane asked for something that I think is probably more necessary than him showing his work. And that's us showing our work. One of the biggest issues that we do have in this community is a lot of talkers and a lot of people that don't understand what they're even trying to say. And it's very refreshing, Totoro, when someone actually does get what's happening and can go, oh, you want me to do it? I'll do it. Last night was very chaotic, so this would never have happened. You could you would never have gotten.
Yeah, it was a little bit all over the place.
And like I said, what I do plan to do is this is for the people listening. I'm gonna see who has the most of it, me or Demon Stride. If Demon Stride has more of it, I'm obviously gonna promote his links in his YouTube channel before mine for this because it was at his house. But if I have more, I'll upload it, or I may give it. It doesn't matter. It's going to get uploaded in the next day, and you guys can see where this stemmed from. But yeah, Shane wants Totoro to show his work before he does. It's been done. I'm going to give this to him. I'm going to send this to him as a fucking as a file. I'm going to send it to him as an upload, and I want him to respond to it.
Well, I mean, we're all sorts of all over the place here, kind of with the argumentation, so it isn't really all that concise. But if you want just a concise version, here it is.
Yes.
We claim that the force of gravity is predicted by this equation, and the acceleration between two objects is predicted then by simply making the kinematic equivalence, or the Newton's first law equivalence being for a specific object, right? So this is going to be the force, mass times acceleration. That's just Newton's law of motion and force. So what I'm going to then say that I want to solve this for a case on the Earth. So I'm going to say that there's a mass of the Earth and the mass of an object on the Earth. These masses cancel, and you end up with rearranging here. It's just going to be gravitational constant times the mass of the Earth divided by the radius square. Plug in all the numbers. Out pops 9.8 meters per second squared. That is the prediction. You can measure that in the lab, and for any object that you plug in, it doesn't matter, any object that you put in, you're going to measure the same acceleration within, experimental plus or minus about a percentage point of maybe a couple of percentage points.
Yeah, I think it's like it's like between like a
9.67.
Yeah,
it's it's typically on the Earth is between 9.78 and 9.83. And it's going to vary slightly depending on where you are whether you're on the equator or on the pole. There's different radius values here and here. There's going to be some shape effects, but really, I'm just looking for them producing this number from whatever they claim the source effect is. If it's density, it's density. If it's electromagnetism, it's electromagnetism. If it's a combination of them, then I would expect them to be able to produce a equation that goes in here that depends upon their electromagnetic effects, that depends upon their electric magnetic, their density effects, their viscosity effects, their whatever effects, I don't know, volume, whatever. Whatever effect they say that is causing this has to come in here, produce the force, and then with that in hand, I'm able to design an experiment. I'm going to take a test mass, whatever, make a prediction, and compare that prediction to the actual measurement, right? So whatever my scale measures when I plunk that on there. So this is the charge they have. And when I asked Shane when I said, I have this, but let's just say for the moment, for the sake of argument, that I don't. Let's say I don't know about this. When I asked Shane, produce this so that I'm able to verify it, he immediately tried to change the subject and shift the burden of proof and say that, well, if you can't produce this, then I'm not gonna even try. And at that point, you know that he's basically standing there holding an empty sack.
Yeah. And that's why, like I said, that's why I wanted you to do it, because now he is adamantly, every time someone asks him to show his work, it's, you show your work first, and then I'll do it.
Yeah, that's just dodging the question. Because I mean, even if we didn't know what gravity is, that does not absolve him of having to explain. Because if he had said, again, to reiterate, if he had said, if Shane had said, I don't know what gravity is, I make no claims to the source, make no claims to the mechanism, I make no claims to the causality, whatever. If he said that he has nothing, then it was said, okay, we're done. I'm not going to press you. I'm not going to force you to do anything. And I'm going to say, okay, you go ahead and research it, then get back to me once you've done the research and you figured out what it is. But they do make claims. They do make claims to the source, the mechanism, the causality, whatever. They say that it's some sort of electromagnetism that's at some bias and it's some density and viscosity and whatever, and relative, I don't know, density, disequilibrium, or whatever. Whatever they say a whole bunch of word salad, but they never produce the actual quantitative prediction. Something that can be tested in a lab. That's how you know real science from crap. If somebody makes a quantitative prediction and it agrees with experiment, you're on the right track. If somebody just has a bunch of waffle and when you ask them to make a quantitative prediction, they try and run, that's how you know you're dealing with somebody who knows they don't got nothing.
Yeah. So it's actually pretty okay. So I think, just for the record, I think we kind of engulfed everything that I'm going to show him. So I do want to make it. Riggs, how you doing, sir? Thank you for joining. If you want to jump in, you're more than welcome. Anybody who wants to jump in, we're definitely complete open panel now.
Yeah, I'm going to shut up for a minute and let everybody else have a chat about it.
Hey, dude, I appreciate the fuck out of this, because this is one of those moments where it's like, it is absolutely been, they asked for something and now they absolutely got it, and I can't imagine any reason besides not having an answer not to respond to it. And then hopefully, see, this is the thing. Someone said in the chat that it'd be badass for you to debate a flat earther, and I think you debating Whitsitt and Shane would be a great idea. The problem is that you would need a moderator that can listen to word salad happen. I can't do that. Like you heard me. I was trying to moderate for you and Shane, but I just have so many questions and I get confused by what he's doing, and he doesn't allow the time for it to be explained.
Right. I mean, to be honest, I don't really feel confident enough in my grasp of all the underlying physics to be able to debate on this in complete confidence. Like I have a layperson's understanding of this.
That's not true.
Stop
doing that.
I can assure you.
Stop. I'm going to tell you right now, that last statement is complete bullshit. You want to know why? Because I am the layman. And I understood 63% of what you did here. and it started at 40, but you did notice I was asking a lot of questions, so my understanding went up. Like I could probably go over this and have and go, oh well, he was saying this and this means this. I could do all that, and I even understand a lot of it because I'm sure you noticed when we got to the electromagnetic part and Witzit's explanation, I knew exactly what the issue was because I that was one thing that I've had a conversation with Witzit once about this, and the second I got to having to fucking ultra fry your nuts to fucking jump, he went into his diatribe, and I can't do the word like last night my brain started hurting.
Runs away. Yeah, he immediately runs away because he knows that if you actually follow through with all the quantitative predictions, it just falls apart.
Yep.
I'm going to tell you why I think that I'm a lead person, because there are people most guys in university that study this are far, far, far better equipped. Like for example, these where's Coulomb's law? On here, there's Coulomb's law. This is actually just a special case or specific solution to a much more general set of 4 equations called Maxwell's and Heaviside's equations. And what those guys are, they're differential vector calculus. And that shit is like on the edge of my grasp of being able to understand. Like the moment a del operator gets involved, I start getting worried.
But see, here's the thing. With that being said, that would also mean that at the even simplest, if they're using Coulomb's law, everything you did under what you just didn't, you squared up, they would not only be able to explain, but be able to explain it in about 3 seconds so they can move on to the good stuff.
Sure. But the thing is, I don't have enough of a grasp on the underlying physics and the actual like Maxwell's equations to where I could trivially derive this from the first principles.
But
Maxwell's equations are extremely they're extremely powerful, but they're also quite complicated.
But here's the problem I see though. They hit brick walls before they get to Maxwell's equations.
Oh no, yeah, no, absolutely. Yeah, absolutely. I have no idea what those are. But the thing is that in flat earth discussions, if I don't immediately put up a full-throated rebuttal with all the details in place, as long as they can throw enough ambiguous shit on the wall, they are presumed to have prevailed. It's just the fundamental imbalance of the shyster versus the actual guy who's trying to give you facts.
Yeah, well, here's the thing that I also noticed. And this is what a honest debate would look like, this stream times 2, because both of them, and I've seen this, when physics professors debate each other about shit, actually I have seen one on gravity, and so everybody knows, I do believe that some of what they're saying is right, but I believe it's going to be due to gravitons, not electromagnetic forces. But I've seen this, and this, all these equations and the discussion, that's what a debate about this specific topic between Shane, Witzit, and Globe. This is exactly what a debate should look like. And
sort of, yeah.
The problem is that when Shane and Witzit do this conversation, you don't see any of this. Shane has come to now the conclusion that you have to show something, but what Shane, can you scroll all the way back up to the top?
Sure.
Shane shows this. Shane shows known equations and doesn't show the connection, the connection, the way he gets from each equation. He can't show you that. He doesn't.
Yeah,
no, I'm not going to say he can't. I'm going to say he doesn't show. The problem with going, look at this rather than this is how I got to it, is that I will never figure that out. And if someone who does figure it out can't show where it's wrong. And that's why asking for them to show their work is so fucking important. Because I can tell you now, I heard Toro Talk say this stuff last night. I heard Shane say a lot of this stuff last night. But in my brain starts melting. Because by the time we get, so you see what's on the screen now, scroll down, just one scroll.
Sure.
By the time we get there, Everything before that, I am now is lost from my fucking brain. Scroll down again.
Mhm.
Now everything above that is, and that's how it works when someone just
Right.
says it, and
Yeah.
that is what I think they play on.
Yeah.
I think Shane realized that. Shane's actually a pretty smart dude. I think he realized that, and that's why now he has all this visual representation for everything. But like I just said, all he's doing is giving you known equations, screenshotting them, clumping them together, and going, "I know this, therefore what I'm saying has to be right." But he's not showing the connections between everything.
Yeah, he's not completely inept at math in that respect. He's extremely, I would say, dishonest in how he's applying it, but that's a different matter. Uh,
Well,
yeah,
I
so
don't think you
I'm
should.
not really,
I
yeah, I don't think I'm really the person to talk to debate on a specific topic to complete exhaustion, like especially not the electromagnetic stuff. What I could debate, I mean, if we were talking, my personal field of expertise is aviation. So if we were talking, you know, southern hemisphere flights and that kind of stuff and how that proves Earth, I'd rip those guys to shreds. But on this,
Yeah, that's
I'm
untouchable for
barely
me.
above. I'm barely above an amateur.
Stop saying that. You say that, and you're. I like that you're saying it, but just know that the world knows that's not true.
I mean, okay, I guess.
You're a smart dude. Just
Yeah.
understand that.
Like I said, in terms of aviation, I'd rip them to shreds, but in terms of this, not really sure.
Okay, so for now, this is out of all due respect. Shut the fuck up for like 2 minutes. I did see Riggs unmute, and I see Extra unmuted. If you, I mean, you guys could jump in now. I know me and him have gone back and forth, but I do.
I really
Go
wanted to
ahead.
keep the conversation clean for whatever cuts you were going to take out. So
Oh yeah, I appreciate that, man. Yeah, we're good now.
yeah,
We're good.
I don't know exactly how to. There is a lot laid out, and much of it I don't understand. And the best way I can kind of interface with some of the things that were said is that like the the paradigm in which you're operating in would have to be somewhat modified. So like if you're going to say that things that on the flat earth side they have to meet these requirements, the requirements that you abide by are defined in such that meet your paradigm. So in order to interpolate those things, you'd have to. It's basically like saying, what does this word mean in a different language? Well, guess what? That language doesn't have that word, and so then it might be difficult in order to have a completely different worldview. So it
But
may not meet your specific requirements in your language. You know.
yeah, I can definitely, I definitely can see where you're saying the issue is, or not the issue. When I hear you say that, I think instantly in my brain that's why we have what we just watched, because math doesn't it's kind of its own language, I guess you would say. So like I see what you're saying. Like in his head, it's the words we're using to equate what we're saying aren't the same as his, but he could be saying the same thing. But that, and I guess that's the reason we're able to even say that is because we don't see any of the work shown to go.
Here,
but
I'll
he
give an
means
example.
That, yeah.
I'm going to give a really, really basic example, and this is like at the one, I guess near the beginning or the middle of his presentation. Like at the beginning, you say, "Well, you need to meet this equation right here, right?" What was it? F equals yeah, just
F,
yeah,
F there, F B
Yeah.
F E F.
What do you mean?
It was
equal-
it was the force law, right?
Yes.
Yeah,
Or
so
no,
this
no,
guy-
it was
Yeah.
yeah.
That's That's the force law.
So-
Let me rewrite it cleanly.
So
So
in
that's-
so in his worldview, right? In his worldview, like there's an effect, right? Or I guess
A causal.
now
so
I'm already
this
getting
is-
kind of confused
so-
between them both.
this so what we're claiming is that this
no,
is
hang on,
no-
hang on 1 second. Because what Shane is saying, so erase the G.
See, I'm not
Yeah.
even trying to say what Shane is saying. I wasn't there for that.
Oh, okay.
I'm
my
just,
apologies.
I know that Shane and I both have, we might have similar, we look at this similarly. And so Shane might have been trying to argue against, it's kind of like when SE was saying, well, if I did believe in the Webb telescope, then
Okay.
you see what I mean? So like Shane might be operating within your terms and saying, well, what about this? What about that? Doesn't mean that he's operating from his worldview. So I don't know exactly how far into the weeds you guys got.
Yeah.
But I can just say this. For example, in this scenario, when you're creating this force law and you say things fall at this specific speed, 9.8 meters per second squared, right? Now, I know for a fact that these people, now they may operate in those terms in order to have a conversation with you. I know for a fact that these people, they don't believe that things fall uniformly, right?
Well,
No,
in that case,
Witsit.
we have a
So
Wait, Witsit and Shane do.
no Witsit. I think Gish gallops. He changes his stance.
No,
depending
wait,
on
wait, wait, wait,
what he
wait.
needs.
But the thing is that the 9.8 ish, I like that term.
yeah,
I've heard both of them acknowledge it very well. They both acknowledge the conclusion.
that's fine. That's fine. I think for the sake of discussion, they don't get into those weeds. But the problem here is I think that intrinsically, if that one specific is not directly true, then they can't speak to you on your terms. So in order to have the discussion, they're willing to concede, okay, this is the effect. But in reality, it's more of a variable. And I do think that they believe that different elements fall at different rates. It's just not really discussed. Okay.
Yeah, I've heard Witsit say that exact same thing, and he will refer to some test done by some university somewhere without actually
it's
being
the
very
ZARM.
specific.
Okay, well, it's the ZARM tower. It's 110 meters tall, and what they do is they pull a vacuum on the whole tower, and there's this slingshot mechanism. Now they don't always use the slingshot. Sometimes it's just raised to the top and dropped. Sometimes it is at the bottom and it slingshots up, and then it just let gravity fall, right? But there is evidence that shows that there is a whole, I don't know, maybe like 10 different elements that have a completely different effect of falling. Now, I think the reason that people just assume things fall at the same rate, or like the average is this number, is because it was agreed upon in the early, like 100 years ago or so, by a committee of people. It was agreed on that we're just going to use this number. It's good enough. Okay, it's a fair value for what we observe. Now, when it comes to the actual elements, I think what happens is that because the air is so thin, in order to actually discern, obviously you'd want to have a vacuum, right, to get the most distilled version of the effect, right? That's the thinking behind your worldview is, oh, if we're in a vacuum, then we can get rid of all these like drag and all this other stuff, right? Now that makes sense to some respect, but at the same time, the problem with that is that if you're going to do that, and there is some variability, then you would need to have an extremely large facility that is in a vacuum in order to even discern any differences between these.
No, not necessarily. No, not necessarily. That's one of the. That's usually where I think Witsit will try and hide the ball whenever the discussion gets to that point. Is that I'm not looking for agreement to 20 orders of magnitude or like 20 significant digits. I don't care. As long as you can get to an agreement to within about 1 to 2%, then we're at least in the ballpark of talking. And you can demonstrate this with essentially a laboratory experiment that you can purchase a lab vacuum chamber for a couple of $1,000 and just put it in a room. So you
Can
can
you build one for a lot cheaper? Can't you build it for a lot cheaper?
No. What I'm trying to say here is that the ZARM tower, they performed this, and within over 110 meters in free fall, it showed, I think, a difference of like within a foot. So we're talking about like an extremely small effect.
Yes.
But there is differences.
Right. So what I'm saying is, but I'm only looking for agreement to within this kind of a percentage. So I don't care if there's more refined reasons. That's okay. There might be finer effects that their force law is going to apply. That's fine. I'm just looking to correlate it to something I can easily test to within a reasonable level of accuracy. It has to produce at least something that is close enough. If we're
Well, let me-
then gonna if we're then gonna go ahead and refine it, we can. But first we have to have agreement on this. So basically, I first have to have something on here before I
Yeah.
can even start.
Yeah,
making
I know, and
predictions.
this is why they don't really go into these weeds, because first of all, you'd have to refine like the argument to even make that claim. So it's easier just to move forward with the falsities after the fact of 9.8 instead of actually going into the whole 9.8 thing. So this is why like your theories end up standing. They have much more legs, is because you basically refined all these like smaller arguments that might actually, like if you looked into it, might actually just fall apart separately, but we would have to have our own version of that in order to replace it, right?
No, I mean
and we don't have that.
no. This this force law, you can test yourself, and as long as you accept agreement, when you probably also want to introduce a centrifugal term here, but you can get this to agree with your measurement to within a percentage point, irrespective of what other. If you exclude properly other effects, you will get agreement with your measurement to a very high level of precision.
Okay.
So it'll agree to within a percentage point. If you then want to propose, so the charge that I'm giving them is for them to propose something that goes here that is based upon the electric, magnetic, and whatever kind of other effects. That is not gravity, because one of the principal properties of gravity, and I can get into this in a little bit more detail a little bit later. I don't want to derail the discussion here.
But that was what I was saying before when I said to erase that G. You want them to replace that G.
No, not just the G part. I want them to replace the whole thing. The G part is basically just a scaling factor. So it's one of the things I've been trying to get into here in a little bit more detail. Is this G is just a consequence of the units that we use for these individual parts here. If we set our units differently.
Oh, okay. So G could be G. So whatever their conclusion is G.
Yeah.
Okay.
No,
Okay. I get it.
what I'm saying is here is that G will vanish, or G will become 1 if you use distance, mass that are not kilograms and meters, but they are more directly correlated to the force of gravity. So essentially, you would be kind of distributing G into the units themselves that you're using, but you'd be using somewhat weird units, so it would no longer be kilograms and meters and newtons.
Have a completely different theory of all things like that.
No. You just have
I
different.
think so.
No. The units the theories would remain the same. Just the units would change, because this is just a scaling factor, just a correction to.
G is simply a constant of proportionality.
Yeah.
That's all G
Yeah.
is.
Okay.
Exactly. So it's like saying that.
So G isn't gravity.
G.
It is a constant.
We call it a constant of gravity just because it relates the scaling of kilograms and meters to our force units, which are newtons. If we use different units here, here, and here, right? So these three, if they were more finely tuned such that the correlation was more direct, then G would actually vanish out of here. Or rather, it would basically get folded into the unit scale. It's just because of the fact that for some reason we've decided that this should be 1/10,000, I'm sorry, it's 1/10,000,000th of the radius, sorry, not the radius, the path from North Pole to the equator through Paris. So we just scaled our units to Earth, which the universe has no obligations to prefer or work with. So it's really, G is just a correction from our preferred units to produce the correct effect on the other side with our other units. But you can actually make it go away if you just use different units. One of the common tricks of simplifying when they explain special relativity is sometimes, in order to simplify time measurements, they will sorry, distances, right? So if you basically want to get rid of some distance corrections and velocity corrections, so v squared over c squared is oftentimes you find a special relativity. Sometimes they will simply define velocity units instead of being meters per second. It'll simply be light seconds. And then you can basically write the velocities instead of being meters per second, they just become fractions of the speed of light. So it's a velocity becomes like 0.5 light seconds, and that tends to simplify a whole bunch of constants out of the equations. It's just I would say it's just a units trick. The same thing for gravity. This constant here is just the scaling factor to get the units to work out.
I have a
Makes
quick
sense?
question. Then I gotta get some food and do some other things. But yeah, so I was just wondering, and you're talking about whether or not you could debate Witsit, but so I gotta ask, does your paradigm account for basic unilateral phase detraction of magnetophosphorence and intertwined lines of etheric flux, combining in a GeO-degaussing modal interaction of non-Euclidean sinusoidal depolarization to produce a polarized Lorentz contraction within the magnetohydrodynamic range of electromagnetics?
Yum yum yum. You got some dressing with that word salad? Because I don't like my salads to just be dry.
They have to have some substance.
Only if you conduct that within a prefamulated amulite casing.
Yeah, exactly. Yeah, you deconfubled the Dusmatron. Yeah, it's that's the thing, is he can gish gallop and he can just throw shit on the wall faster than I can rebut it.
Yeah, okay.
G does have one odd little thing about it though, and that is the units that have to be associated with it. You can't just take G away. You can't just make it 1, because then all you've got is kilograms squared per meter squared. That makes no sense. That's not a force. G has the dimensions of Newton meter squared per kilogram squared.
Do too.
So
okay.
kilograms and meters go away, and you're left with newtons. That's sort of important.
Very important.
So it's
Very
a physical
important.
constant in that sense.
Yeah. Yeah, I suppose, yeah. So I guess, yeah, you might need to have some other conversion factor in there. Let me think.
Yeah, the number could become 1 instead of 6.67 times 10 to the minus 11th.
Yeah.
If you pick the right mass and the right distance for M and R, but you're still left with the fact that it's got to be in the units and in dimensions of.
Yes, the dimensions need to be corrected for. Yeah, you're right. So in that case, yeah, you might not be able to get rid of the constant completely. You just need some unit conversion factor.
Yeah.
And really, I guess that's kind of an indication that the effects of gravity are somewhat more, like the causal factor is not necessarily. This equation basically just correlates some input parameter. You might think of mass as a gravitational charge and a distance, but there might be some mechanism that actually gives rise to gravity underneath that we don't understand. We just abstract away by using the constant here. So yeah, I'm sure, and this is sort of high-end, cutting-edge physics. I'm sure those guys would say, no, you're using the completely wrong equation. It should be something that's a lot more generalized, and in that case, you could probably get rid of all constants. But whatever. This is fairly, at that point, you're very much into the postdoc work in university departments.
Well, you get rid of Coulomb's constant the same way.
Yep.
Do you understand all that, Blue? What was it? The Maxwell equation stuff?
Yeah. It's well, you're going a little beyond high school level physics, which is what Shane can do.
Yes. This is basically, at this point, we've not left high school so far. This is basically all just division multiplication.
Yeah.
Once you get into Maxwell's equations, you start getting into vector fields and the curl and the slope and all that kind of stuff.
Mm-hmm.
I never got into physics in high school.
Me either. I'm learning a lot of this. You put better understanding into a lot of it.
Yeah, unfortunately, most physics teachers they're just trying to get through the day. I guess they might have some motivation in trying to explain this to students the first couple semesters, and afterwards it just yeah, kids have a tendency of pulling all the enthusiasm out of teachers.
Some
So yeah,
teachers, because just
some
remember,
teachers. I mean,
to
some are.
remember, because
Yeah.
look, because here's the thing, you got to remember, I am self-taught. Um, all those, a lot of them are guys like Blue, Paul, Gravity. There's a lot of guys that actually sat down and talked and didn't lose that enthusiasm. And so I got to learn a lot, and I got to learn everything that I know about this stuff is through you guys. Not even has nothing to do with school. Anything to do with school, I don't even fucking remember. Let's be honest.
Yeah. Yeah, that's
So
unfortunate consequence of, yeah, organized learning kind of has this tendency to just try and pump out students and just be done with it.
well, I think
And they don't.
that's the biggest issue with this argument that we're having.
Mhm. Yeah,
I would
could
say
be.
the majority of the people that have these conversations with anybody who has an alternative thinking
Mhm.
has only a basic high school education. And here's the thing. I think, and this is going to sound weird, but I think their basic high school understanding of physics is less than mine, because I have all the in betweens, the questions
Mhm.
that aren't asked in classes, and I've watched lectures in classes and stuff, and heard professors and how they talk and what they expect in a classroom. You don't get this. You don't get the but what ifs. What this doesn't make sense. What I think it could be. You don't get any of that conjecture back in a class. That I think where the people here are learning and getting to learn get that opportunity. I think that's important.
To be fair, in a classroom, you don't generally have all the time because there's just so much material
Mhm.
you got to get through, and you don't have the time to babysit each and every question. So you kind of just have to breeze through it and just get it rammed
But
into students' heads so that
but
they
that's
can
the thing though.
regurgitate it on test. It's a little bit sad to be honest.
But that's the thing though. So like I said, I don't really remember much of high school.
Hmm.
But I got B's. I got A's. Like I wasn't. I learned very easily. You don't have to know anything they teach you. You just got to remember it. And there's a big
Hmm.
difference between what I just said. Um, Luckily, I found this 10 years ago, and I had the opportunity to not just remember it, but actually start learning it. And from what I remember, kinda, and what I've heard information come out of a lot of what we call Glober's mouths about this stuff. A lot of it is the information without the questioning. Like you can tell that what they got is what they read off Google or remember in high school. And I think there's so much more to it than just that. The questions, the doubt, all that is important because that's how we even got to this point. The questioning and
Sure.
doubting.
Yeah, absolutely.
But
One thing by the way, I want to bring up one thing before I go. I got like maybe 15 minutes. Hopefully, I'll get through it. Um, One thing that I kind of always had an issue with Shane's argumentation is his constant contention that the only way, what's he talking about? The only way we've determined the shape of the Earth is from stars, or some variation thereof, some nonsense like that.
that we have used the planographic view of the stars to shape our Earth. That is what he
Right.
claims we've done.
So he always claims that we go from stars to Earth, which is complete horseshit. Um,
That's
and
impossible.
it's it's not just impossible, it's stupid because we have completely independent methods of verifying the shape of the Earth without ever referring to stars ever.
Yeah,
This does
you
not
don't have to look up.
necessarily need to happen.
You don't even have to
Yeah,
look
you don't
up.
have to. Yeah, you don't have to look up. So the classic example, the thing that you can do in an auto level is you can literally just do reciprocal zenith angle observations. So literally you just determine the direction of up, but you don't actually look at stars to do that. And then you just do horizontals to each other, sight the thing, and measure the angle here.
Well,
Or rather,
another
measure the angle
important thing
from
that I
zenith.
remember from these conversations is that when you have that planar, because that's what it's called, the planar orographic view of the sky from Earth. If you, and this goes exactly with what you're drawing up right now. If you take both of their views of the sky and you put it into a mapping form, you'd get a sphere, because each person's view gives that, or it would model out to a sphere. So you can model out our globe based off the stars. It'd take a lot longer. You have to actually be at different locations to do it all over the world. So it's very difficult to do. But if you mapped out what he's talking about, it would map out a globe, because just the view of it and the where the stars on the edge of your view would be compared to where the other person's are, it wouldn't work on a it just, the perspectives wouldn't line up.
Yeah, he that's where the kind of model he stole from Walter Bislin is where he needs to have light doing completely crazy shit and taking turns that are insane in order to like match it to a flat Earth. But so there's kind of the zenith observations or reciprocal zenith angle observations are the classic example. Let me show you another one. And this is kind of more subtle, I guess, but it's also something that is absolutely mathematically provably correct. So there's a area of differential geometry that was worked.
I gotta go get food and dust off my kayaks. So.
All right, sir.
Have fun
I'll go later. Yep.
I am a little bit jealous about that part.
Okay, so one of the areas of differential geometry that Carl Friedrich Gauss worked on had to do with the study of shapes embedded in 3D space. And so one of his conclusions is he called it a remarkable theorem, or he called it in Latin, because that was the language of the learned world back then. He called it the theorem egregium, so the remarkable theorem. And essentially what that says is that if you have any surface, so let's draw a surface here, whatever, something like that. And for this surface, you can actually calculate a property on it, which is called the Gaussian curvature. One of the fundamental discoveries of Gauss is, first of all, that this Gaussian curvature is invariant. You cannot change it by doing anything with the shape without distorting lengths, angles, and basically like shapes on the surface. So as long as you want to preserve all of these, then Gaussian curvature remains invariant. You cannot get rid of it. Makes sense so far?
Yep.
It's a property. It's a property of the shape. And the theorem, what theorem egregium specifically says is that you can determine the curvature of a surface
by putting a triangle on it.
by simply measuring distances and angles on that surface with no reference to the outside frame, to the outside space in which it is embedded. And so this is typically called Euclidean three-dimensional space. So basically, it's just a fancy name for saying it's a right angle coordinate system that has straight axes, right?
Yes.
So,
but
each of these
what happens is the second you get to your results conclusion of this, you notice there's a problem. That problem is that nice little triangle you've made does not equate to 180 degrees.
Yeah, well, the triangle conclusion is one of them. But
that's why I was saying, like, you drew that out, the first thing I thought was, oh, put the triangle on it.
Yeah, that's one way to do it. A triangle, yes, indeed, and that is a direct consequence of Gaussian curvature. Another thing is you don't even have to lift your butt off your chair. You can literally just go, hey, I'm gonna measure the amount of time it takes to circumnavigate the Earth from New York to, I don't know, I did it for Cairo in Egypt to Beijing to LA back to New York. So you sum this up.
You're
Then
in
you do
aviation,
another.
right?
Yes,
You're
I'm in aviation.
So I'm going to
Yep.
show you something real quick that I first of all, I know you know this, Dr. or Blue Marble. I know you know this, and I will always thank Dr. Bob for showing me this. What you're showing, the the best visual representation I've ever seen in my life, and I will always use it. Oh, I gotta go to Discord. Hang on, I gotta do this first so I can share it. There it is. Is this good old Sky Vector?
Oh yeah. I
Shout
might have
out to
showed that.
Dr. Bob. Dr. Bob showed me this originally, where he showed me
Yes.
how to do all the flight plan thing and all that.
Oh, yeah.
And basically, what it ends up doing is it literally. Oh, damn it.
Yeah. It'll give you distances. Yeah.
Yep. And then it will show you exactly what we're talking about when you do your the flight
Yeah.
route out thingamajigger.
Mm-hmm. Yeah, yeah. You can just type into the departure and destination in there. Type in into the delete both of those fields, departure and destination, and type in at the top. Type in KJFK, yeah, and delete the route as well. Yep. At the top, put in KJFK, and destination also put in KJFK. KJFK.
And the bottom one's same.
KJFK, yes.
Okay.
Okay, so this is JFK to JFK. Now we want to actually make it a circular route. So just put into the route and type into the route HECA. That's Cairo.
HECA.
HE.
HE. Yeah.
Yeah.
CA.
Heka. Yeah. HECA.
Okay.
Heka.
Okay.
Space. ZBAA.
ZBAA.
ZBAA. Yep.
Okay.
That's Beijing. And KLAX.
And that is LA.
That'll be it. Los Angeles. And so this is going to give you the total distance. And if you make the same route in the south with similarly spaced airports, you're going to get essentially the same distances. And crucially, you can also then connect the distances from each of these guys, from like the southern ones, like from Johannesburg to Beijing, Cairo to Sao Paulo, that kind of stuff. You can find flight routes, and you can measure out all of these distances. By the way, funny story is you don't even have to use Sky Vector for this. You can literally just do it from Flight Radar 24 just by flight times. If you average those together, you're gonna get an average of flight times, and those are also going to be essentially the same value one way or the other. And the shape, if you look on my stream here, the shape that this makes is not embeddable onto a flat surface without like massively distorting the planet in some completely unrealistic manner.
Okay.
To where you would have like, by the way, you could probably just even do Santiago. There might be like routes to Cairo or Santiago to LA or stuff like that. You can even truss it up with more routes, and then it just becomes completely rigid, and it literally forms a 3D shape. And no matter what you do, the consequence of theory Mike Region says, no matter what you do with trying to deform this, somehow embed it into a flat space, you cannot do it. Not without distorting either the lengths or the courses between the routes. In fact, you probably wouldn't even be able to do it even if you distort its courses. So it just ends up completely an impossible task to do. And this is a direct consequence of the fact that the Earth's Gaussian curvature is not flat. It's not zero.
Okay, I'm gonna ask a question, and tell me if this is like so off the rail. Okay, the same situation you described, isn't it the same situation that describes the universe as flat?
The description of the universe as flat is a little bit more nuanced. It's yes, that is one way I guess you might describe it, but the way that they describe the universe as flat has more to do with the four-dimensional space-time curvature.
I feel like
not
it,
on.
and correct me if I'm wrong. I feel like it's they express it as flat because there are too many discrepancies otherwise.
The
So
argument is
so
quite a bit more.
yeah, it's not
The
flat. It's like
I
because
know, no, no, I know what you mean. I know what you mean. You mean
yeah,
like it has a net zero curvature of space-time. That's
yes, and
essentially the
and
argument.
and here's and so people that are listening, so people that are listening understand. There are consequences to it not being,
Yes.
and there are things that I know are added in just to make sure that number does it stays that way. Because if it is negative curvature, then we
Mhm.
have this really bad situation where at some point in time we're all fucked. Not us, the universe. Like it's going to do this thing called the crunch, and that's what
Big rip.
Einstein
Big rip.
rip. There you go. Sorry, and that was kind of like what everyone thought was going to happen. Then when they started looking into it more, what actually they see, and there's a lot that goes into this, so I'm going to just kind of throw little bits in so it makes more sense. Imagine how everything makes a gravity well. So if you looked into the distance, and this is an imaginary time, if you're in space and you were looking and you could see the fabric, right, and you could see each mass creating a gravity well, you know how you would see less of the object because it's kind of sitting in the fabric. Well, what we actually see is that we actually see things kind of just disappear the further out it goes. The problem is that would create what they call a saddle. If that is the case, then what we see out there is fucking wrong. Everything's fucking wrong. Speed of light, everything's fucking wrong. If it's saddle.
Mm, not. I mean, not quite. It has some cosmological consequences, but those are really so far beyond the discussion about the shape of the Earth.
Oh yeah, no,
By
no,
the
yeah, oh
time,
yeah,
yeah.
yeah. Hang on, yeah. This right here has nothing to do with Earth. Nothing to do
Right.
with the
Okay.
shape.
Um,
Nothing at all.
so one of the classic examples, or one of the classic explanations for why they think that the universe is flat, is because it is essentially an implied consequence of the expansion rate of the universe slowing down but never stopping. That is, if the expansion rate of the universe is slowing down and never stopping, but it's slowing down continuously, then what it says is you can formulate an energy equation such that you have essentially like the kinetic component of the expansion subtracted with the gravitational component of it being contracted back. And as long as the universe, if you think about like this is time,
Mm-hmm.
and this is the size of the universe, as long as it essentially expands, there's a limit to its size. Let's call this, some limiting size. It slows down and slowly approaches that limit, but never quite reaches it. What that would imply is that these two quantities
Mm-hmm.
are precisely equal, and therefore the total energy of the universe would be zero. Make sense?
Yes.
And so,
Everything would essentially not stop, but
yes.
I'll essentially have to make
Mhm.
figure out how to make space for time
Mhm.
continuing.
No, what it really means is that the universe could essentially start from nothing. Like if the universe's energy is total energy is zero, and there's no law in physics that says you cannot make something, so to speak, out of nothing as long as you obey some conservation laws or some balance laws. So say for instance, there is no law that says, in fact, there is a law that says very much that you should be able to do this, and it does happen. There is a type of nuclear decay. You have a neutron at the start. And this type of decay is called a beta decay. And what that does is it converts a neutron into a proton, so a positively charged particle. But here's the problem. One of the conservation laws of the universe says that um, electric charge must be conserved. So what that basically says is that if you sum up the charge here and you sum up the charge at the end, they both have to be equal. Make sense so far?
Equal. Okay, yeah.
They
Plus one.
both have to be the same at the start. No, they both have to be same at the start and at the end.
But
right?
But how's that?
Right.
That okay?
Yeah,
So
that's
okay.
that's what left out.
Okay, yeah. That's
a
this
neutron
is the,
decaying into a proton.
Wait, hang on. But this would be the creation. This is creation right here.
This is nuclear decay. This is really a thing that happens on the daily, but
in a sense, for
the
what
way
we're talking about, you're talking about the
like
process
that.
of this starting over.
Well, that's just sort of. I'm trying to just explain conservation laws in general.
Okay.
So the way that the universe does this is it generates an electron out of the proton. So the electric charge, here it's negative, here it's positive. It's the same charge magnitude. Sum them up, 0. So this system still has net zero charge.
Okay.
But you've generated a new particle.
Okay, I'm back on board now. Okay, I get it now.
So you've generated a new particle, so to speak, out of nothing. You know what I'm saying?
Yes. Okay. Yeah.
And so that is sort of the argument here, is that if the total energy of the universe is 0, if you do some accounting, basically the way in a certain way, then you might say that you are able to generate a universe out of essentially nothing. Now it's a fairly preposterous, and it's not at all, I would say, a settled argument. This is mostly hypothetical and speculative physics. So.
But this is what happens when their calculation is run on a saddled universe.
This is
positive,
for the flat
positive.
No, this is for the flat universe, for zero curvature. The positive universe actually is a problem because the positive and the negative curvature universes have a problem here.
Yeah.
Because this becomes non-zero.
Oh, okay. Hang on. Okay. So you were. Oh,
so
okay.
Fuck. If there's an excess amount of kinetic energy, then you're in the saddle case.
Yeah. Okay. So
and
what you were just explaining is
gravity.
Yeah, what you were just explaining is kind of where we're at and how it.
Yes.
Well, we already think it is, right? Don't they look at?
We think that the universe overall, the geometry is flat. Mm-hmm. So we think that the overall
wait.
of the universe. Mm-hmm.
I thought it was positive. I thought they.
Hang on, I'll explain what I mean. I'll explain what I mean. There's a confounding factor that is currently unexplained, and everybody kind of just is sitting there scratching their head, or their ass, I guess. This is sort of the expectation of classical cosmology. Here's the problem. When we measure the distance versus the redshift, or essentially the velocity of recession.
Yes.
Of very distant objects, what you would expect is for it to essentially follow a linear relationship.
Green.
But you know that it doesn't.
It'd be like green, blue, yellow, red. That's what we expect.
What we're talking about, like redshift being basically the velocity going away. It's just cosmologists talking redshift.
But there's a visual representation of that.
It's more red, basically, more towards red, more towards longer wavelengths.
As it goes further
away. But the problem, yeah. And the problem is that we're observing this.
Rapid. Okay. Yep.
Yeah, we're not rapid. It's actually fairly subtle, but there's an increase the further away an object is, a disproportionate increase in the speed of its recession.
And this is the idea that when we see a star traveling away from us, what is happening is not.
This is
galaxy.
This is galactic. Okay. This is galactic scale.
Okay, we'll just say object. It is not only at speed, but it is increasing.
Yes.
Okay.
And
with the current cosmology, quote unquote, the Big Bang, there's no reason that they think that at this point it should not still be increasing.
Well,
it's not. Well, things aren't increasing is a problem. We're seeing things that are slowing down.
Yeah, it should either be this, or if the universe had negative energy, that would be that. But the problem is, it gets a little bit more complicated than that. But the problem is essentially that we're observing this in very distant supernovae. So in supernovas that are, by the way, distance scale here This is not individual stars ever. You're not going to be able to measure stars. Well,
No, these are
supernovas.
clusters. Yeah, these are clusters.
These
yeah.
are galaxies really that we're observing, because in terms of distance scales here, we're talking billions of light years, so gigaparsecs.
Oh,
So this
which
is
brings me to this. When we get done with this, I'm going to show you guys some images of a friend. Okay, so a friend of mine live streams. He's like a UFO guy. Like he's all into that shit. He's really good friends with he's a professional astronomer. Has his own setup. Blah 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 blah. But the other night we were looking at the sky, and I got to watch literal live time him track and look at nebulas and shit like that. I'm gonna show that shit after this. That just reminded me. You were talking about galaxies and stuff. It's pretty badass. The guy's name is Mark something. Fuck, I had it written down.
But yeah, in any case, the practical upshot here is that we have currently no direct working mechanism for this part. We call it for the time being dark energy, but it's sort of more of a placeholder name for we don't know what the hell's going on here. And dark energy is a bit of a problem in that if you model this out on a conventional setup, what you end up seeing is a consequence that dark energy is essentially kind of, if you take everything out of, let's call this a cubic meter, right? So this is 1 meter cubed. It's about, this person sitting down will be inside of this kind of a box.
I got a question. There's a friend flat earther in the chat. What is the universe expanding into?
It's not, the universe isn't expanding in like a balloon expanding into, well, not a balloon expanding into a volume. So it's not like this. I know exactly what you mean, and it's kind of a mind bender. So it's not like the universe is a bubble here, and then it gets bigger, and it gets bigger, and then it gets bigger. But there's some other space out here, like that's just empty space. It's much more productive to think about this. Think of it this way. It's not that the universe is expanding into something. It's rather that lengths, the scaling, the scale factor of the universe is changing over time. So if you had a light ray that you emitted and it had a wavelength of 1 meter, if you wait long enough, then it's going to be 2 meters. The same light wave, you've not done anything to it. It's just been traveling or been bouncing back and forth between 2 mirrors or whatever. Let's assume that you can make a light wave that never stops, right? And just keeps bouncing back and forth, back and forth, back and forth. What's happening is that the universe's scaling component is going up. So what used to be a meter before is now 2 meters. And it's going to be eventually changing and expanding more.
I think the best way to say it is we don't know.
I mean, ultimately, of course, the actual answer is, yeah, we don't know enough about many factors in cosmology to be sure. But
I mean, the issues that we're talking, because what we're talking about now is a cosmological issue. It is.
Yes, this is cutting edge stuff, and to be honest, fairly speculative. So we don't need any of this in order to discuss the shape of the Earth.
No, not at all. This is I took it way off into the weeds for no reason, but it's what because it actually is important because that what we just talked about is actually one of my arguments that I had when I was a flat earther.
Right. Yeah, I understand.
As in a sense of if you can't explain this, how are you? Because it's not the same topic. It's not the same. It doesn't. You can't really have the same conversation when you're talking shape of Earth and the shape of the fucking universe. But what it does is I used it subconsciously to discredit what you know about science. Because if you don't understand, and again, they don't understand, and I didn't know this part. It's science being honest and saying we don't fucking know. This is what
Yes.
we think. This is what we've come up with so far, and this is what we've observed due to what we've
Yeah.
predicted. And it's
Yeah.
really not a situation where they're ever going to go, oh fuck, we figured out the edge of the universe is. That will never
47th
be
Street
known.
past the
Yeah.
lamppost.
Yeah, if anything, that would probably be the one thing in science I can say we will never know. We will never
Yeah.
know. We just won't.
Well, I mean, there is the currently all scientific understanding points to there being like this is our visible bubble,
Mhm.
and if you wait long enough, eventually that bubble sort of, so to speak, grows just because of the fact that more and more light gets to us, so we'll be able to observe it. But at some point,
Ah,
the expansion rate of the universe is faster than the light is able to travel towards us. So essentially, there is a cosmic limit to our knowability. So this is the knowable, or more directly more accurately described as the interactable
yeah. So what would happen is you draw a
universe.
circle. So that line
Yeah.
is. You could also draw.
Yeah.
You can also draw. You can also draw 300 billion years.
Yes. So this is the limit of how far we will ever be able to interact with anything else in the universe. There might be other stuff out here, and it's very likely to just be the same stuff typical of the universe. The universe. That's why they say that the universe might very well be infinite in size. Like we don't know.
Yeah.
We know
Well,
the
the biggest issue that we
limits of
have.
our.
Yeah, the biggest issue right now we
It's going to be
have the cosmological background, which is that circle.
Well, not quite. The cosmological background is actually this part here.
What?
And
that's what's within it.
And that's the thing that's essentially receding. No. You're thinking about it a little bit in terms of like classical mechanics and time and stuff. When you get to these sorts of time scales, distance is essentially a measure of time. So when you're looking at the CMB.
Yeah. So hang on. So yeah, when we're looking at a star, we don't go, that star is 1,000,000 miles away. We say that star is 200 million light years, which means it took 200 million years at light speed to get here. So we made a defining line of where that distance, or what that distance would be.
Sort of. So when you're talking about reasonably small distances, within a few million light years, you can basically kind of sort of ignore the time component for most purposes.
So yeah, we've seen it for the light's gotten here a long time ago.
Not so much. I mean, the light that you're seeing right now has just gotten to us.
Yeah.
So the star is, let's say, I know that this distance is 2 million light years. So I know that its clock is plus 2 million years atoms compared to mine, right? So this is my T, and his T2 is essentially my T1 plus some number. But the distance is sort of independent of that. But when you start getting into extreme distances, you're talking billions of light years. At that point, time and distance start to become a little bit entangled. So let's say this distance here is 20 billion light years. And you're questioning now, hey, wait, hang on. How do we compute that? Because we say that the universe is only 13.7 billion years old, so billion years, right? So how can this be? And the long and the short of it is that even though currently the object is that amount of distance far, the light was emitted less than 20 billion years ago. You following me so far?
And we're just seeing the continuance of it.
So when the light was emitted, the star was a lot closer.
Yeah, when it hit our eyes.
Yeah, less than when it started its travel, that's when the light started on its way.
I'm sorry. Yes.
Since then, the star has receded to a much larger distance, and the light actually has had to travel actually somewhat against the expansion of the universe until it got to us some value less than 13 billion years later. But by this time, the star has actually moved quite a bit further away.
And we see And we measure that by the intensity of it, of the light we're
If you're talking about the distance measurements, that gets a little bit more complicated than that. There's the thing called the cosmological distance ladder, where we are able to observe objects essentially right out to the outer limits of the visible universe. And what what I want to mention here is why we say that the observable universe as it is right now for us, we say that it is approximately 96 billion light years across. So that's what, 48, is it? Yeah, it's 48 one way, 48 billion light years one way, or the radius part, right?
Yes.
But we only said it's 13.7 roughly billion years old. So the question then is, how does that happen? Well, when the light actually, and this is the CMB, by the way, this is the cosmic microwave background.
Okay.
That's essentially our limit of seeing.
Limit. Yeah.
It was a whole hell of a lot closer when it started its emission, and the universe has been slowly expanding past that, beyond that envelope, and the light was trying to get to us. It was slowly being dragged along as well, but it still overcame the expansion and got to us some 13.7 billion years later. But by then, the actual CMB is quite a bit further away. Or rather, the point that generated that surface is quite a bit further away.
So what? Okay, so if it didn't move, let's say the universe wasn't expanding,
right,
we would get
static.
Yeah, we would get we would get
exactly the same.
Mathematically and visually the numbers would stay the same. But what we're getting is our math is showing this, our observations are showing this, and when we look in the other direction, it happens twice over.
Yes.
Okay. And so the expansion is the explanation for an observation that mathematically should be further.
Yes. And the reason is that when you look at stuff along our distance ladder, we see it receding faster and faster away with distance, and it's based upon that distance. It's essentially the linear progression of that distance that we know that stuff is receding away from us, so that we know that when we see light, that is, for simplicity's sake, we're going to say that it's 13 billion years old. We know that the emitting object is a whole hell of a lot further by now.
Yeah.
But and the reason why the CMB expands, it's not directly the expansion rate of the universe. The CMB is actually expanding faster than the expansion rate of the universe, because the CMB is not it's not a single thing. It's not an object. It's not a sheath.
It's a result of
like, yeah, no, it's the CMB is more the phenomenon of us seeing back into the past. So what you're seeing here is the universe as it was about 300,000 years after the Big Bang. So by that point is just about when its temperature dropped sufficiently low that it became transparent to radiation. Before that, it was opaque. Opaque in the sense that the entire universe was just too hot, and there was no atoms that have been captured. So basically, any radiation couldn't make it very far; it would immediately be scattered off.
Okay, so basically, in layman's terms, it'd be like shining a mag light in your face, and over time, adding one of those particle boards with the holes in it, slowly adding it in.
Think of it more like this is water, this is air, and try and shine a flashlight in water. It's going to go a little bit, but it's not going to get very far.
Yeah.
Okay. It's going to essentially get absorbed by the water. But at some point, 300,000 years after roughly the Big Bang, the water evaporated and became air. So the flashlight can now shine
a little bit further. Yeah.
Well.
Okay.
Essentially, it's a vacuum. It's a neutral vacuum, so it's essentially infinite. But yes.
Yes. Yeah.
So that is how that got generated. And the reason why we say that it was too hot back then, but right now, by the way, when you measure its temperature, it's about 3 Kelvin. It's only 3 degrees above absolute zero. It's because of the fact that it has expanded by that much. And the radiation used to be extremely short waves. It would have been like X-rays. It has from the time it has traveled and the universe has expanded so much that the radiation that gets to us is so low energy that its radiation temperature is essentially 3 Kelvin, or the black body radiation temperature, or whatever. You get the point.
Okay. Yeah.
And so literally, the light has been stretched out and its energy has been reduced, and that's how we explain the expansion of the universe. It's not that the universe is expanding into something, rather that the density of the energy in the universe is getting lower because
Yeah.
its volume is going up. So that's going up, and therefore the density of stuff is going down.
So essentially, what it expands in isn't even
Itself.
It's not
space
it's
is
not
part of the
it's,
universe.
Yeah, it's not a question, or a better way of saying it is, it's not a question of what it's expanding into. It's more of a question of how it's expanding.
Yes, it is itself expanding. It's the space itself that is changing scale.
Yes. Okay.
But again, this is cutting edge,
yes,
fairly
yes,
speculative
yes.
cosmology.
Yeah, because I was gonna say, there's a whole faction that explains why that happens, and say that the universe is finite. There is an edge. I've never heard one of them claim to where it is or how far, but they say there is one. And the way they have explained this, and I'm pretty sure you're going to instantly know what faction says this, is that there is plasma gases within the universe that give us a false reading on what these stars are actually doing. Because they believe that these stars could be halfway out from the center, and our reading is giving us the C and B reading.
Yeah, it's the plasma, the electric universe people, right? Those guys.
Yes.
Yeah, they're complete nuts.
Which
I mean, they're not really
which correlates. What correlates, because I believe, and I've heard someone outright ask the person and them say no, but Terrence Howard is an electric universe.
Yeah, no, they're nutters. And they're not taken seriously anywhere in academia, really, because
have you seen? Well, they're not.
They do hold the Terrence Howard interview.
Yeah, the recent one where he sat down with an actual physicist.
I have not actually. No, I haven't seen that one. I've seen the one with Joe Rogan, and I've seen a bunch of rebuttals where people essentially are laughing at him. Mm-hmm. But I've not seen him debate a physicist.
It wasn't a debate. What happens is it's So Joe Rogan has a guy come in. I forget his fucking name. I've been watching it. But the guy is not there to destroy him. He wants to work with him, and he cleverly explains over and over again what Terrence's issue is. And Terrence has the same thing a lot of us have. Not you at all. Myself, probably Shane have, where when you self-teach yourself something, terminology and path to terminology start skewing. So when someone like yourself or like Big Blue Marble hears it, it sounds like word salad. It literally does. But there's an understanding in the person that's actually saying it. And I think this is what is actually really happening with like Shane and them. The problem with them is, and if you watch this, you'll notice right away, there is a difficulty in what happens when you try to explain someone this. This has happened to me. When you try to explain to somebody that you're on the right path, you are not stupid. But what you are saying is incoherent to the people you're trying to perceive this to. That's where I think flat Earth and globe and physics and pseudo starts. And that is what's happening with everything. I think that's the problem. And that is why I was saying what I really want to do is I need you to be confident that you are a fucking super genius, because you are. And when you align that with the fact that I'm stupid, it makes it we bring the middle, the layman, the real layman, because you're not fucking layman. And I'm stupid. I'm below layman. I'm stupid, but we make the layman.
Okay. Okay. Well, in any case, I got to run here.
Yes.
Thanks for the chat.
Absolutely.
Enjoy the rest of your stream. And
I'm about to end it. I appreciate it, man. Every time. I definitely appreciate it. Thank you, sir. You have a great rest of your weekend.
It's a pleasure. You too.
Yep.
Cheers. Bye.
All right, people. I'm going to wrap it up. That was exactly why I live stream. I got to experience this now. That was fucking great. I loved it. I want to make something clear. The main reason for this live stream was because I do plan on clipping and getting it out to Shane. Or if Shane's willing to watch the whole thing, I hope he would, but I doubt he will. But Shane literally asked for Globers to show their work when it comes to their reason things fall explanation. And I noticed last night that he wouldn't really give way for it. So I wanted to give Totoro an opportunity to give way and him do what Shane asked, us show the work. And then the best part is I had Totoro show what Shane was expressing and be able to explain where the issue with Witsit and Shane and their idea of what the problem is. Because we've heard their explanation for it. That we don't really need to hear that part again. It's very important that we understand that now we're at the point where we want to see work shown for it. Luckily, there are people in the community that can show the work, because I would have never been able to do that. But it was in a way that I can now understand it. And I can say, this is why. This is what we're asking for. This is why we're asking for it. I understand that 100% now. Whereas in last night, I really didn't. It was more of a confusion of what Shane was trying to say. And because like I said, I recorded it. And when I listened back to it and I realized what Shane was doing was bypassing things by saying other things, I thought it would be great to be able to actually break it down. And again, like I said, we just did a 3-hour or 2.5 hour stream based off of, I think it was a minute and a half of what Shane said. And I want people to understand, if what you just watched, I hope if you're listening, you watched it. That is exactly what a debate between Shane, Witsit, would look like against someone who understands what they're talking about and is arguing with them about it. I think the biggest problem that we're not seeing is that there's no work to show for it. Shane does have what he calls peer-reviewed stuff, explaining how he derived 9.6, I think is what he got. The problem is you're showing equations and you're not showing your work. I would like him to show not his work now, but show where what Totoro put out was wrong. Show where when he did describe what you were saying, he was wrong there too. And I think that would get us a lot further in this conversation about whether or not this downward bias has anything to do with gravity, electromagnetic density, relative density, specific gravity, correlating functions of a factor molecule 6 on the third scale of a Euclidean 6D geometry. You know what I mean? The reality of it is there are ways of explaining these things. It's not so much on the listener to know exactly what someone means. It's the person that's getting it out, the information out there, right? It's on them to show that they can explain it so that it can be understood by all, not just themselves. And again, it can be just for themselves, myself, it doesn't matter. But if you're going to say you are wrong, therefore why? I think the showing your work part isn't so much to say you're wrong. It should be a way of showing how right you are, right? If you've come up with these mind-breaking, these mind-numbing, life-altering things in our perception of reality, I would expect anyone who is giving that perception to be able to show how they got to that. Not just say, I did this, this, and this, now believe it. You should be able to have a structured way of going, all right, I'll spend a half hour, 45 minutes, and I will show you exactly with questions how I did this, because this would be from that person. I understand exactly how this works. And that goes with anything in life, right? Whether it's, I know how to do this, show me. Well, if you're going to show someone something, you're not going to go, well, just do this and then walk away. You're going to show them detailed way of how to do it so they understand your way of doing something. Just showing your work isn't a gotcha. It should be your gotcha. But yeah. With that being said, guys, I like I said, I was going to show you these. So I'm going to show you guys this slide of the astronomy astronomer. There you go, astronomer that I connected with. These are some of his images. I will put them in the links to the description to his website. It's pretty badass. He has a million pictures. He has his own observatory, whole nine. But he's connected with a buddy of mine that's into UFOs. So they do a lot of like UFO stuff. It's pretty badass. I'm going to try to get connected with him a little bit better and maybe get an interview, because he said the other night he does like doing interviews with people that aren't really into it, because he wants people to understand this. But the guy I'm talking about, his name is Mark. But this guy's like been on Ancient Aliens. Actually, let me show the pictures while I talk about him. This guy's been on like Ancient Aliens, doing forensic analysis of cosmological data that they got or perceived to got. I'm not really sure how that part worked, but yeah, let me get to so you can see more. So this is the cluster galaxy. I think he was saying there's millions of suns in this one. This one was pretty badass. Here's the badass part. So the observatory that he built for it is like 1,000-something miles away, but he has other cameras there, so it has different views of stuff. But he was like going to different stars and everything, and he was showing the different focal lengths and the different plates and shit, so you can see like as the progression of it getting there. Fucking shit was amazing. I forget what this one was called. I think this was the Omega cluster or some shit. Or Mega, I don't know. There's a bunch of binary stars. Pretty badass. This was pretty cool. This is a galaxy. I don't remember the name of the galaxy. I have it written down, but I'm not looking at those notes. These are the badass ones. And this is real-time shit. Like, he was showing us real-time observations. Or is it, there it is, the pillars. And I guess what's called the Eagle Nebula. I think that's the next 5 pictures that I'm going to show. I just thought these were fucking amazing. It's a close-up one of it. This one's badass. And he was showing like how like the focal length and the exposure that gets these things, rather than it having to be like one of those things where globular cluster, not really a galaxy, more like a blob of stars. Galaxies are about 3 orders of magnitude larger, billions of stars instead of just, okay, my bad. Thank you for the clarification. But yeah, he was explaining, let me show you. I want to make it bigger so you guys can see what I'm talking about. Like this guy, he was like explaining where like if you see the Eagle Nebula, right, where it's like looks like a little mouth and then there's a star in its mouth. He was explaining like how the distance between the star and the gases, how it burns it off and creates those and forms those little columns. It was pretty badass. This guy, he was pretty fucking smart. I gotta figure out. I'll get his information. I'll put it in the description for sure a little bit later on. But yeah, I thought you guys would enjoy that. There's so many more that I want to show you guys. Those were the quick ones that I showed, knowing that I'd be doing this. Why is my background not working? That's weird. Okay, so like I said, guys, I'm going to go ahead and get out of here. We had a fun, long stream. I do appreciate Totoro for doing that and showing his work, like Shane asked, because now there shouldn't be any reason for that. I will get that out to him, and hopefully we'll get a response and/or maybe one day have him here. I don't know. I don't think Shane likes me very much. We'll see. But with that being said, guys, I'm not going to do any more rambling. I'm just going to go to my intro and say peace.
Disagrees with experiment, it's wrong. And that simple statement is the key to science. It doesn't make a difference how beautiful your guess is. It doesn't make a difference how smart you are who made the guess or what his name is. If it disagrees with experiment, it's wrong.
Yeah, Look, they said that I couldn't do it, so I went and did it. W's only, you know I've been winning. Top of the world, the globe is spinning. If you know, you know I've been on a mission. Go. Okay, let's get it. Got a little time on my hands like a wristwatch. I don't got time for the brakes and the pit stop. Race through the gridlock, take it like Chris Rock. Right to the chin, still win. Heavy metals like Slipknot. Got the driving, I got tunnel vision. I just hit my stride the way I run the business. I've been making paper like I'm Dunder Mifflin. See the end game, I got one division. Look, I don't ever bother with a critic. Hit him with a chronicle of Riddick. Boom, bottle full of Ritalin. I hit him with a little bit of riddle me this, riddle me that. My bad, fell asleep at the gas. No time to wait though. Elon Musk, I'm trying to bankroll. New Tesla just cause I say so. Electric whip like Ivan Van Gogh. I just did it. W's only, you know I've been winning. Top of the world, the globe is spinning. If you know, you know I've been on a mission. Okay, let's get it.
I've been on a mission like totally spice. I'm bad she bad, but she totally nice. Nails are blue and her toes feel like white. They complete me, match out at the soul for my leg. You knew it for sure, but